Hello, friends, and welcome back to the Snoozy Scientist, where we gently explore the mysteries of our world, one sleepy yawn at a time. Wherever you are on this vast and beautiful planet, this space was made specially for you, a calm corner where science and curiosity can sit side by side to guide you softly into a deep sleep. Tonight, we are traveling back to a time when Earth spent more than 1 billion years lifeless, a planet that appeared stable on the surface, yet remained completely empty. For ages beyond imagining, Earth was silent. No animals, no plants, no microbes, not even a single strand of DNA drifting through its oceans. Only young seas simmering beneath toxic air, while meteor after meteor struck with enough force to sterilize whole coastlines and strip the atmosphere bare. And yet, almost as soon as the bombardment faded, something began to change. Life appeared quickly, far more quickly than scientists believe should have been possible, rising out of conditions that seemed designed to destroy anything delicate enough to grow. Every living creature that has ever existed, from blue whales to insects to humans, traces back to a single microscopic ancestor that appeared only once in all of Earth's history. But those earliest cells were not primitive at all. They arrived with membranes, metabolism, and genetic instructions already working in concert. Even though no natural process is known to create such complexity from lifeless molecules, scientists have searched the universe for decades, mapping stars, planets, and distant worlds. Yet nowhere have we seen chemistry transform into biology. Earth remains the only example we have, and the first traces of life show up almost the instant the oceans cooled, as though something rare, urgent, or briefly perfect had taken place. Studies reveal that if early Earth had been slightly hotter, slightly colder, slightly more acidic, or slightly less stable, the delicate conditions required for life might never have formed. Life began once, survived against impossible odds, and never started again. But why did a lifeless planet manage to cross this boundary at all? What hidden moment allowed simple molecules to learn how to copy themselves? How did coordinated systems appear when nothing in nature suggests they should? And if life began only once, what does that mean for every world beyond our own? Tonight, we follow the faint trail of clues left in stone, ocean, and cosmos, drifting gently toward the moment when Earth first learned to live. But before we begin, if you enjoy these quiet journeys into wonder, I'd love it if you gave this one a gentle like and maybe tapped subscribe. It helps more curious minds, just like you, find their way to this calm corner of the internet. And if you're still awake enough to type, let me know in the comments where you're listening from and what time it is where you are. It's always a joy to see how far across the world this little sleepy corner of science travels. So now take a deep breath, let your shoulders loosen, and together let us step softly into the mystery of how life began. Long before the first fragile hints of biology stirred in the oceans, Earth lived through an age shaped almost entirely by fire. The young planet turned slowly beneath a sky filled with thick clouds of darkness, its surface glowing with rivers of molten rock that never seemed to rest. Even from a great distance, Earth would have looked restless, as though it carried a fever that could not break. Volcanoes rose and collapsed in cycles that lasted ages, sending fountains of bright magma into the air and letting ash drift so high that sunlight often dimmed before it could reach the ground. The atmosphere that wrapped the planet was heavy and wild. It held no breath a living thing could use. Instead, it swirled with choking vapors, the kind that clung to the ground in thick folds and stung the surface of every cooling stone. Clouds formed not from gentle water vapor, but from the fumes of sulfur and metals driven upward by violent eruptions. Lightning flickered through these clouds again and again, bright veins cutting across a sky that rarely stayed still. The air carried heat the way a furnace does, holding it close, refusing to let the planet cool. Amid this harsh world, the crust continued to shift and settle. New land appeared in the glow of lava and vanished soon after, swallowed by the moving mantle beneath. There were no continents, only scattered pieces of solid ground drifting across an ocean of molten rock. These early fragments cracked easily, allowing fresh magma to spill onto the surface and keep the landscape in constant motion. Nothing stayed familiar for long. Even mountains had short lives, rising and sinking in spans that would feel like moments compared with the ages that would follow. Yet above this churning surface, something softer began to gather. As the planet rotated through uncounted days and nights, the heat slowly leaked into space. Each degree lost allowed a little more vapor to cool, twist together, and fall as rain. At first, the drops were tiny and short lived. They evaporated before they touched the ground. But slowly, year by year, the balance shifted. The rain thickened, then strengthened, then turned into storms that drummed endlessly on the rock below. The sound of that rain must have echoed across the young world, falling on land that had never known water. These storms continued for ages. They filled cracks, carved small channels, and gathered into spreading pools. More vapor cooled, and the clouds released their weight again and again. At last, the first true oceans began to appear, still hot and restless, yet steady enough to settle into the deep basins that gravity molded for them. They steamed into the sky, and their surfaces shimmered beneath the dim sun. It was in these waters that the earliest building blocks of chemistry would one day dance, but for now they were far too hot and far too unstable to hold anything delicate. Water did not arrive through rain alone. Beyond Earth, in the cold dark of space, comets drifted like frozen travelers. Some wandered close enough to be pulled inward by Earth's gravity, breaking apart as they struck the glowing surface. Their icy cores added more water to the deepening oceans, and with them came carbon-rich dust and tiny molecules forged in the quiet of interstellar clouds. Asteroids did the same, carrying minerals and simple ingredients that would one day matter, though at the time they only added to the chaos. The collisions were violent enough to boil oceans and send vapor roaring back into the sky, repeating the cycle again and again. For millions of years, the environment remained too severe for organic chemistry to take hold. The heat was relentless. The ultraviolet light from the young sun cut through the atmosphere with ease. Even the oceans, though growing deeper, stayed near boiling. Molecules that tried to form were torn apart as quickly as they came together. Paths that would one day lead to proteins and strands of genetic material could barely take a few steps before dissolving back into the water. The world seemed determined to prevent anything fragile from enduring. Still, the cooling continued. Bit by bit, the atmosphere thickened with new gases released from volcanic eruptions, and these gases began to shield the surface from the most harmful light. The crust strengthened. Vast regions of molten rock dimmed into solid stone, allowing the first long-lasting land masses to rest upon the mantle without sinking. The oceans lost their violent steam and began to darken into calmer basins. Rain fell with a gentler rhythm now, washing minerals from rock and carrying them into the sea, where they swirled together in endless motion. With this gradual cooling came something precious. Temperatures dropped enough to let molecules linger instead of breaking apart. In the still warm but now stable waters, carbon compounds could drift and collide without vanishing in an instant. The air, though still toxic by modern standards, no longer stripped the oceans bare with every eruption. Volcanic fire still flared across the horizon, but its power no longer erased all progress. Earth had entered a quieter, more patient stage of its history, the planet no longer roared with constant violence, and it breathed in longer rhythms, cooling just enough to nurture reactions that had never been possible before. Within this softness, the earliest whispers of complex chemistry began to take shape, sheltered by the oceans that once seemed too hostile to allow anything to form at all. The world was still young, still uncertain, but it was finally ready for the first fragile steps that would one day lead to life. As the young planet settled into a quieter rhythm, a soft haze gathered above its surface. The violent heat of earlier ages had faded, leaving room for new shapes in the sky. The air, though still far from gentle, carried a different kind of weight now. It wrapped the world in a mixture of carbon dioxide, nitrogen, and drifting water vapor, all rising from oceans that no longer boiled with every breath. These gases formed wide bands of cloud that shifted with the slow turning of the planet, catching traces of sunlight and letting them scatter across the landscape in muted colors. Within this atmosphere, simple molecules wandered freely, carried by winds that wandered from sea to land and back again. Methane moved through the air in thin streams, joining the faint scent of ammonia that rose from volcanic basins. Hydrogen sulfide, released from cracks in the crust, added its own signature to the mixture. Together, these ingredients created a world rich with reactive possibilities. They were small, light, and easily broken apart by heat or sunlight, yet they rebuilt themselves just as easily. In their constant rising and falling, they shaped an environment where chemical stories could begin to unfold. Across the planet's surface, the oceans breathed in these gases. Waves curled over one another, drawing in carbon dioxide and letting it mingle with minerals washed from the rocks. Sunlight touched the surface of the water and stirred delicate interactions that would have been impossible during the planet's hotter past. Each day, a new balance formed, slight but growing stronger. Molecules left the air, entered the sea, drifted for a moment, then returned to the atmosphere once more. It was a dance that repeated endlessly, a quiet exchange between sky and water that helped seed the earliest chemical pathways. While these interactions shaped the world from within, other ingredients arrived from far beyond Earth. In the wide silence of space, carbon-rich fragments drifted on ancient orbits. Some were small as grains of sand, some as large as mountains. When they fell toward Earth, they brightened the sky in long streaks before striking the ground or slipping into the oceans. These meteorites carried their own collection of organic molecules, including amino acids that had formed in the cold darkness between stars. Many of them broke apart upon impact, releasing their contents into the surrounding environment. Others dissolved slowly in water, sharing their complex structures with the seas that cradled them. Scientists today still find remnants of these visitors in preserved stones, their patterns containing clues of early organic chemistry. The presence of amino acids within these ancient fragments offers a glimpse into the kinds of materials that helped shape the planet's future. Though small, each molecule added to the growing reservoir of ingredients that filled the oceans and coastlines. With every fall of cosmic dust or crashing impact, the collection grew richer and more varied. Along the shores, where land and water met in long meandering lines, the planet's surface breathed in a slower cycle of its own. Pools formed as waves retreated, leaving thin layers of water behind on warm rock. Sunlight dried these pools gently, concentrating the molecules within them. Then the tides returned, refilling the pools and allowing the ingredients to spread once more. These wet and dry rhythms repeated day after day, shaping the shallow basins into natural laboratories. During the drying phases, molecules that drifted alone in dilute water were pressed closer together. The heat of the day coaxed them into forming bonds that could not have arisen in deeper, colder regions of the sea. As night arrived and the pools cooled, those new bonds held firm. When the water returned, it carried the newly formed chains into the larger ocean. Over countless cycles, these simple reactions began to create structures that were more durable and more intricate than anything the planet had held before. Even inland, where rainwater collected in small depressions carved by ancient storms, similar processes took place. The pools swelled, shrank, then swelled again, each change allowing molecules to meet and part in new ways. Some arrangements fell apart as quickly as they formed, others lingered, slowly increasing in complexity. The rocks themselves played a role, offering mineral surfaces that steadied fragile interactions. Clay particles held molecules in their tiny layers, giving them a place to rest long enough to assemble into new shapes. Iron and sulfur minerals added their own textures to these chemical landscapes, guiding reactions that needed a sturdy foundation. Through all of this, Earth continued to cool, allowing the ingredients to gather without being swept away by overwhelming heat. The atmosphere thickened slightly, softening the light that reached the ground. The oceans deepened, creating pockets of quiet water where chemical structures could drift undisturbed. On coasts and in tide pools, the steady pulse of wet and dry conditions encouraged longer chains to form, then break, then form again. In the sky, methane and carbon dioxide continued their slow cycles, feeding the world below with a gentle rain of reactive energy. Nothing alive moved through this world yet. There were no cells to carry instructions or divide into new forms. But the pieces that would one day shape such things were gathering in silence. They traveled in the wind, settled in the sea, soaked into the soil, and drifted along every shoreline. The planet had woven a tapestry of raw materials, each strand waiting for its chance to play a part in the unfolding story. Within this wide and patient environment, chemistry began to stretch in new directions, guided by the steady rhythms of Earth's early days. As Earth continued to cool and gather its raw ingredients, the planet entered a long twilight of experimentation. Nothing alive moved through its oceans or traced patterns across the land, yet the world itself behaved like a quiet laboratory. Every wave, every gust of wind, every flicker of light carried energy that touched the tiny molecules drifting in water and air. With each touch, something subtle shifted. Bonds formed, broke, and formed again. The planet was practicing, trying countless combinations in a slow and patient search for structure. Much later in human history, a scientist named Stanley Miller would recreate a small echo of this ancient world. He sealed water, gases, and sparks inside a glass chamber, letting them swirl in a miniature storm. Within a short time, simple amino acids appeared, the same types found in proteins that shape every living creature today. His work became a window into the chemistry of early Earth, a reminder that the building blocks of life can arise from ordinary ingredients when energy stirs them in just the right way. Though Miller's experiment was a distant imitation of the real environment, it revealed that nature has long been capable of weaving complexity from simplicity. On the early planet, energy poured into the environment from every direction. Lightning split the sky in branching patterns that illuminated the landscape for heartbeats at a time. The bolts reached down again and again, striking ocean and land with the force of sudden heat. With each strike, the molecules waiting in the air and water reshaped themselves into new arrangements. Ultraviolet radiation from the young sun traveled through a thinner atmosphere than the one we know today. Its rays carried enough power to jolt electrons loose and allow atoms to assemble into unfamiliar structures. Volcanic gases rose from deep within the crust, carrying with them the restless heat of Earth's interior. Sulfur, Carbon and metal-rich vapors mixed with the air and changed the chemistry of the world with every eruption. This energy played two roles at once. It was a creator that allowed new bonds to form, turning simple molecules into chains that gathered meaning. Yet it was also a destroyer, breaking apart those same chains when it grew too intense. Molecules that survived one moment might vanish the next, lost in storms or dissolved by heat. The planet showed no preference for preservation. It simply offered opportunity and let the outcomes decide themselves. Through this constant rise and fall, a quiet truth emerged. The experiments were countless, and even though many failed, they created a landscape where rare successes could endure long enough to grow. In the oceans, molecules drifted through layers of warm water that churned slowly as winds pushed the surface. Sunlight traveled through the upper reaches, gently warming the waves and giving some reactions enough energy to continue. Deeper down, cooler currents sheltered fragile chains that formed during the day. These chains lingered, waiting for the next moment of warmth to help them stretch or twist into something new. Over time, the oceans became rich with dissolved carbon compounds. Each tide pulled more from the shore, mixing it with minerals carried from distant volcanic regions. Along the edges of the sea, small pools collected near the rocks. They held thin layers of water that thickened with organic material as the sun dried them. Molecules gathered in these shrinking basins until they touched one another more often than they did in the open ocean. Some formed tiny rings, others built short chains that drifted in slow spirals when the water returned. Minerals in the sediment steadied their movements, holding them just long enough for new bonds to appear. The pools glimmered with faint activity, not visible to the eye yet busy in ways that mattered deeply to the future. Inland, where rainfall filled hollows carved by ancient lava flows, something similar unfolded. The pools warmed under sunlight, cooled at night, and repeated the cycle with gentle patience. Each shift in temperature encouraged different reactions. Some favored the creation of longer chains, while others broke those chains apart to make room for new attempts. These small environments acted like pages in a notebook. The planet wrote chemical lines, erased them, then wrote again, leaving subtle traces that guided the next attempt. Wind carried aerosols across valleys and ridges, letting droplets rich with organic compounds settle in distant places. When they landed on warm stones, the water evaporated quickly and left behind thin films of molecules that continued their quiet experiments. Rainfall collected those films again and returned them to the larger pools. The landscape moved its ingredients in a slow and rhythmic dance, spreading complex structures across wide areas. Though nothing living had emerged, the planet had begun to hold a memory of its own. In oceans, in pools, on stones warmed by the sun, the first hints of organization appeared. They were small, transient, and constantly reshaped by energy, but they endured long enough to matter. Chemistry was finding footholds in a world that, for the first time, was cool enough and gentle enough to allow them to remain. In this patient environment, Earth continued its work, letting the earliest threads of complexity drift, settle, and take shape in the quiet spaces between light and water. As Earth's earliest molecules drifted through warm oceans and gathered along quiet shorelines, the planet continued its long search for structures that could hold meaning. Many chains formed and vanished in those ancient pools. Some held together only for a moment, while others lingered long enough to explore new shapes. Among these wandering threads, one type slowly revealed a talent that set it apart from the rest. It was flexible yet orderly, delicate yet capable of remarkable tasks. Today we call it RNA, a molecule that would one day help all living things read, copy, and share the instructions of life. At this early stage, the world knew nothing of genes or cells. It knew only the constant turning of chemical possibilities. Yet within that turning, RNA emerged as a molecule suited to bridge the gap between simple chemistry and the faint stirrings of biology. Its structure allowed it to bend and fold like a piece of soft wire, creating tiny pockets and surfaces that could guide reactions. At the same time, it could store sequences in a long chain, each link holding a small bit of information. This rare combination, the ability to hold a message and to act upon it, gave RNA a special role in the earliest steps toward life. Scientists imagined that, in the quiet corners of Earth's young environment, short strands of RNA might have formed slowly. They would have begun as scattered fragments, knitted together by chance in shallow pools or on mineral surfaces warmed by the sun. Once formed, these strands could fold into shapes that encouraged reactions between nearby molecules. In some cases, the RNA strands might have helped assemble new copies of themselves, though imperfectly. Each attempt added variation, letting some versions persist longer than others. It was not yet evolution in the full biological sense, but it held the seed of something more. Evidence of this remarkable ability still lives within modern cells. Hidden among the complex systems that support life today are small pieces of RNA that act not as messengers but as catalysts. These ribozymes cut, join, and fold other molecules with gentle precision. They are like quiet echoes of a much older world, a time when RNA may have performed many of the tasks later taken over by proteins. Their presence is a reminder that RNA once held far more responsibility, shaping the early steps of life long before DNA or proteins became central players. In living organisms now, RNA works side by side with DNA. DNA stores the long-term blueprint, while RNA carries short messages and helps produce proteins. But in the earliest moments of Earth's story, DNA likely had no place. It is a more stable molecule, but it requires complex systems to build and maintain. The young planet held no such systems. RNA, with its ability to form spontaneously under certain conditions, may have been the first molecule capable of guiding chemistry towards something that resembled inheritance. Yet, even as RNA demonstrated promise, it faced difficult challenges. It was fragile, breaking apart easily when exposed to heat or reactive chemicals. Sunlight could damage it. Water could unwind or degrade it. Its building blocks, called nucleotides, did not form easily in a single setting. They needed specific conditions to appear, and those conditions may have been rare and fleeting. For every strand that lingered long enough to fold and act, countless others dissolved before discovering anything new. The world had to offer protection, pockets of shelter where delicate structures could survive for more than a passing moment. Mineral surfaces may have played one such protective role. Clays could cradle nucleotides, pressing them close enough to link into longer chains. Small pores in volcanic rock might have shielded them from harsh sunlight while allowing energy and water to flow through in gentle pulses. These spaces created a balance between exposure and safety, giving RNA a chance to form and explore its abilities. The tides, too, contributed to this process. Pools that dried under the warm sun concentrated ingredients, then filled again with cool water, offering repeated opportunities for RNA to gather and grow. Even with these natural supports, RNA's path was uncertain. Its instability meant that any progress could be lost quickly. Strands might fold into useful shapes, only to unravel when the environment shifted. The spontaneous formation of long RNA chains remained a rare event, one that required a fortunate blend of ingredients. Yet, over great stretches of time, luck accumulated. Reactions repeated themselves millions of times, perhaps billions, until a few strands found a way to persist long enough to matter. Those early strands were small, nowhere near the length needed to carry complex messages. Still, they represented a turning point. They held fragments of memory in their sequences and carried abilities in their folds. Each fold influenced a reaction, and each reaction helped shape the conditions for the next. Slowly, the planet's scattered chemical experiments began to connect, guided by the quiet logic encoded within these fragile molecules. As the ocean settled into broader patterns and the atmosphere softened its intensity, RNA continued its slow dance through Earth's young environment. The molecules moved with waves and followed currents into hidden spaces. They broke apart, then rejoined. They assembled short chains, then tested their shapes in warm pools. Through countless cycles, a few forms proved steady enough to linger, holding the threads of early chemistry together in ways no molecule had done before. In this calm, patient world, RNA played its subtle part, carrying both structure and information in a single, delicate chain. It was one of the first storytellers on Earth, shaping the language that life would one day learn to speak. As the world continued its slow, patient weaving of molecules, a new kind of quiet transformation began to unfold. The oceans that once held only scattered fragments of chemistry now carried richer mixtures. Pools along the edges of warm coastlines thickened with ingredients gathered through countless cycles of tide and rain. In these calm and shifting environments, something subtle but deeply important started to take place. The smallest building blocks began to reach toward one another, forming chains that lingered longer than anything that had existed before. Amino acids, shaped earlier in the planet's storms or delivered gently by passing meteorites, drifted through shallow waters like tiny seeds waiting for the right conditions. In the open ocean, where waves stretched endlessly and dilution softened every interaction, they often passed by one another without connection. But along the quieter edges of the land, where puddles warmed under the sun and then dried in the wind, the amino acids found themselves pressed closer together. As water evaporated, the molecules touched, twisted, and at times joined into short chains known as peptides. These peptides were simple compared to the elaborate proteins that life would one day create, yet they were the first hints of structure that could hold form for more than a moment. The sun played a gentle role in this process. As daylight warmed the stones beneath the shallow pools, heat lifted the water upward, leaving behind concentrated layers of dissolved materials. Within these layers, amino acids found new opportunities to connect. During the cooler hours of night, dew and returning tides replenished the pools, allowing the newly formed chains to drift free again. The rhythm of drying and refilling acted like a soft heartbeat, encouraging bonds to form and giving them space to settle. Nearby, another family of molecules was exploring a similar path. Nucleotides, the tiny components that make up RNA, had begun to assemble in fleeting clusters. Their journey toward becoming long strands was even more delicate than that of amino acids. Each connection required just enough energy to hold them together without breaking them apart. In deep water, the bonds dissolved within moments, undone by constant motion, but on the surfaces of certain minerals, the story changed. Clays, with their thin layers and charged surfaces, offered a place where nucleotides could gather. They held the molecules like pages in a book pressed together by time. Within these narrow spaces, the nucleotides aligned and linked into short RNA strands. These strands were modest in length, forming incomplete messages that held only the faintest echoes of the complexity to come. Still, their existence marked a shift. They represented not just isolated molecules, but threads capable of carrying information from one moment to the next. Iron sulfur surfaces, born from deep volcanic activity, provided another kind of support. Their rugged textures created pockets where molecules could settle and react. These minerals helped guide polymerization, the forming of longer molecular chains, by offering energy in subtle bursts. Tiny patterns of heat and mineral charge nudged the molecules into arrangements that water alone could not provide. The reactions that occurred on these surfaces were slow, shaped by the quiet flow of hydrothermal fluids that seeped through cracks in the crust. Yet over time, these environments built structures that drifting molecules could never achieve on their own. Water, despite being the cradle of early chemistry, also presented one of its greatest challenges. It surrounded the molecules with comfort, but it also broke the very bonds that life needed. Chain formation in water was like trying to build a tower on shifting sand. Each new link risked being undone before it could support the next. This fragility made the sheltered spaces on minerals and the drying pools along the shore essential. They created conditions where polymerization could occur in rare but meaningful bursts. The planet seemed to offer guidance through its natural cycles. Where water flowed steadily, molecules remained safe but separate. Where water retreated, molecules gathered and reached for one another. Where minerals lined the ground, chemistry gained a gentle nudge towards structure. And where heat pulsed through the land from deep volcanic roots, the added energy helped scattered components explore new possibilities. Through countless repetitions, short chains formed, drifted, broke apart, and formed again. Most vanished without leaving a trace. A few persisted long enough to discover shapes that held together. These shapes might have folded into loops or spirals, allowing them to interact with surrounding molecules in ways that encouraged further growth. In this quiet dance of connection and release, the earliest whispers of order began to resonate through Earth's young waters. As strands lengthened and peptides found firmer bonds, the chemistry of the world became more layered. The oceans held not only isolated building blocks, but clusters of chains that behaved differently from the molecules that made them. Some drifted in small currents like threads waiting to be woven. Others settled into mineral cracks, protected from the wide sweep of the sea. Nothing alive yet stirred within these environments. Still, something had changed. The planet was no longer filled only with scattered ingredients. It now held the beginnings of structure, the first soft steps toward complexity, and within these steps, Earth carried the quiet promise of forms that would one day learn to grow, divide, and remember. As Earth's early chemistry grew more intricate, a quiet shift began to unfold along the surfaces of its warm shores and within the sheltered pockets of its young oceans. The world had already gathered building blocks and stitched them into delicate chains. Now it needed a way to hold those chains together, to give them a space of their own where reactions could unfold without being washed apart by the restless tides. In this search for structure, a new kind of molecule entered the scene, gentle in form, yet powerful in its promise. These were simple fatty acids, tiny threads with one end drawn to water and the other turned away from it. They drifted into the oceans from volcanic regions, from chemical reactions fueled by heat, and perhaps from fragments delivered by meteorites wandering through space. At first, they scattered freely, moving through water with no purpose. Yet their nature made them behave differently from the other ingredients swirling around them. When they met one another, they aligned in quiet patterns. When the water grew still enough, those patterns closed in on themselves, forming small circles, and when the circles tightened, they folded into hollow spheres as soft and thin as bubbles. These early membranes were simple compared to the layered walls that living cells would one day build, but they carried the essence of what a boundary means. Each fatty acid sphere created an inside and an outside. The water within was separated from the water beyond, and for the first time in Earth's long story, chemistry could unfold in a protected space. These tiny spheres were not alive, but they were the first pieces of the puzzle that allowed life to imagine itself. The formation of such spheres happened without deliberate guidance. The molecules arranged themselves naturally, shaped by the gentle push and pull between their attraction to water and their desire to avoid it. When enough fatty acids gathered in a single place, they organized into a thin film. When the film curled inward, a sphere was born. These spheres could be small as grains of dust or large enough to shimmer faintly in shallow pools, but all of them followed the same simple rule: water on the outside, water on the inside, and a fragile wall holding them apart. Within these spheres, molecules that once drifted freely through the environment found themselves enclosed. Chains of amino acids, fragments of RNA, and clusters of minerals were trapped inside purely by chance. Yet this chance created something profound. Encapsulation gathered the ingredients into tiny pockets where they could interact more often and with greater persistence. A peptide that might have wandered alone for hours instead found partners nearby. An RNA fragment could fold and unfold without being scattered by waves. The protocells, as these early structures are now called, did not control what entered them, but by collecting molecules in one place, they allowed new reactions to occur. Some protocells formed along the edges of drying pools, where sunlight thickened the water and concentrated the fatty acids. Others appeared deeper in the oceans, near mineral surfaces that released gentle energy and helped stabilize the delicate membranes. The boundaries were flexible, bending with currents and sometimes merging with one another. When two protocells touched, their walls could fuse, allowing their contents to mix. This merging offered more opportunities for chemical growth, letting scattered pieces of the early puzzle combine in ways the open ocean rarely allowed. Yet membranes also revealed their fragile nature. Too much heat could cause them to unravel. Too little fatty acid in the surrounding water made it hard for them to repair small tears. Salt levels, pressure, and even slight changes in temperature influenced whether a protocell survived or drifted apart. Stability was never guaranteed. Still, the world offered countless protected places where protocells could endure long enough to gather meaning. Pools that warmed during the day and cooled at night gave them time to settle. Hidden caverns near volcanic shores sheltered them from sudden storms. Even the movement of tides, which could destroy some protocells, created new ones with each return. The importance of membranes rests not in their ability to exist, but in the quiet order they provided. A membrane gives a space where reactions can stay connected, where progress made in one moment is not lost in the next. Without boundaries, every new creation is at the mercy of the world around it. With boundaries, even fragile chains can begin to take on roles that shape the chemistry inside. Membranes allowed patterns to form, break, and form again within a protected environment. Over time, the protocells that lasted longest did so because their membranes held steady through subtle challenges. As more protocells formed and dissolved throughout the oceans, a slow kind of exploration took place. Molecules tested their abilities within these tiny worlds. Some reactions grew more efficient when held together. Some arrangements of chains helped strengthen the protocells themselves, making the membranes less likely to fall apart. Gradually, the relationship between chemistry and container deepened. The protocell was not life, but it created the conditions that life would need. It offered warmth, protection, and a place where memory could begin to root itself. In these quiet, drifting spheres, Earth learned the value of a boundary. Within their thin walls, the first hints of order found a home, sheltered from the wide and restless waters that shaped the surface of the young world. As protocells drifted through the young oceans, the world around them glowed with quiet power. Heat seeped through cracks in the seafloor, minerals shimmered beneath soft currents, gases rose from deep within the planet, offering steady streams of energy. Earth, still shaping itself from the inside out, created an environment rich with chemical opportunities. Before any true cell learned to copy its information, the world taught chemistry how to feed itself. In those early waters, hydrogen moved like a patient traveler, slipping through rocks and dissolving gently into the sea. Sulfur drifted upward from volcanic regions, carried as both gas and mineral dust. Iron settled along the ocean floor in wide, rust-colored plains, waiting for reactions that required its strength. These elements did not need the presence of living organisms to interact. They reacted naturally, releasing energy as they shifted from one state to another. The earliest protocells floated directly above these ancient sources, bathing in currents filled with subtle warmth and reactive power. Some of the molecules trapped inside protocells found themselves altered by this energy. A strand of RNA might bend differently when touched by iron. A short peptide might fold into a shape that allowed hydrogen to attach for a brief moment. These interactions were not planned, yet they created small cycles where molecules changed, returned to their original forms, then changed again. Over time, these repeating cycles began to resemble the slow heartbeat of metabolism, even though no cell yet existed to guide them. Imagine a protocell resting near a warm mineral vent. Inside it, tiny structures drift gently. If a molecule meets a surface rich with iron, it might accept an electron and change its shape. That new shape might allow it to interact with a second molecule, passing the electron along. The second molecule might release a bit of energy as it settles into a new state. The protocell gains nothing conscious from this exchange, yet the energy can support other reactions inside. When the cycle resets, the pattern can continue, each step opening a door for the next. This quiet repetition allowed protocells to host small chemical networks that echoed the rhythms of metabolism long before true life began. Hydrogen was particularly important. When it met carbon-rich molecules, it could release energy that warmed the interior of a protocell. Sulfur played its own part. In some environments, it offered a steady flow of electrons that helped reactions continue without sudden interruption. Iron acted like a patient conductor, guiding electrons from one molecule to another. Together, these elements created pathways that let protocells use energy without needing sunlight or oxygen. They depended on the deep earth, on heat and minerals, rather than on the wide open sky. These early cycles were fragile. A shift in water pressure or a sudden change in temperature could break them. Many protocells carried no such cycles at all. But wherever the cycles did appear, even faintly, they gave structure to the chemistry inside. Molecules that once reacted at random began to settle into routines. Those routines helped certain protocells linger longer in their environments. They resisted dissolving. They kept their shape more easily. They allowed chains of RNA or peptides to remain intact long enough to explore new folds and functions. As time passed, protocells with more stable cycles drifted into new environments. Some reached cooler waters where the mineral content changed. Others arrived near the edges of volcanic regions where hydrogen and sulfur were plentiful. These journeys allowed the internal chemistry to meet new combinations of molecules. Reactions that began as accidents gained subtle guidance from the shapes of the protocells themselves. Eventually, certain structures inside began to favor reactions that supported their own stability. They did not decide to do this. The world around them simply rewarded cycles that kept the protocells intact. This gradual guidance laid the foundation for something remarkable. Once chemical cycles became reliable, protocells were no longer at the mercy of random reactions. They gained a soft form of control. When certain molecules entered the protocell, they triggered reactions that made use of available energy. When the environment shifted, the cycles adjusted, slowing down or finding new pathways. It was the earliest hint of regulation, a gentle steering of chemistry that would one day evolve into the complex metabolisms found in modern cells. Many scientists believe metabolism took shape before genetics because energy must be harnessed before information can be preserved. A strand of RNA that cannot maintain its structure will dissolve, no matter how clever its sequence. A peptide that cannot fold because the environment lacks energy will drift apart. Early metabolisms provided the warmth and stability needed for genetic molecules to survive long enough to matter. They created islands of order in a world that was still wild and unpredictable. In time, these metabolic patterns allowed protocells to move through chemical landscapes with greater persistence. They could gather molecules, reshape them, and release byproducts that subtly altered the environment. Long before any living cell learned to copy its instructions, the world had already built small systems that fed themselves from Earth's natural energy sources. These systems did not leave fossils or direct traces. Their presence is known only through the logic of chemistry and the quiet rules that shape all life today. Within these early protocells, Earth rehearsed the art of sustaining itself. Metabolism, even in its faintest form, created warmth and structure where none had existed. It helped the first delicate chains endure, guiding them through cycles of change and giving them the stability needed for the next steps in life's unfolding story. Far beneath the surface of the young oceans, where sunlight faded into quiet darkness, the world held landscapes unlike anything above. Tall chimneys rose from the seafloor, shaped by mineral-rich waters heated deep within the earth. These structures breathed warmth into the cold depths, sending shimmering plumes upward like underwater smoke. They were known as black smokers. Their waters were acidic, rich with metals, and hot enough to reshape the minerals they carried. Not far away, other openings released gentler streams. These were alkaline vents, softer in temperature and filled with water rich in carbon compounds that flowed through delicate networks of stone. Each type of vent created its own world. Black smokers erupted with bursts of energy, their plumes dark with iron and sulfur. Their chimneys grew quickly as minerals settled around the openings, forming towering structures that resembled underwater cathedrals. Around them, life would one day flourish, supported by the intense chemistry of their waters. But in the earliest chapters of Earth's story, they offered something even more important. Their heat and minerals created thousands of tiny reactive surfaces where molecules could meet. The environment was turbulent and rich with potential. Alkaline vents, by contrast, created a gentler kind of landscape. Their waters flowed through labyrinths of minerals shaped like honeycombs. These structures were filled with small chambers, each one connected by thin openings that allowed water to pass slowly between them. The walls were made of iron, sulfur minerals that shimmered softly, guiding the flow of chemical ingredients with quiet patience. These chambers acted like natural laboratories, sheltered from sudden waves and steep shifts in temperature. Within these mineral landscapes, a unique form of energy pulsed constantly. As hot, alkaline water met the cooler, more acidic ocean, natural proton gradients formed. These gradients were like invisible slopes made of charged particles. In modern cells, similar gradients drive energy production, helping to power life's internal machinery. But long before cells existed, the vents created these chemical slopes on their own. They offered a steady current of energy that could nudge molecules into forming new bonds, then support the reactions that followed. Imagine a single chamber inside an alkaline vent. It is small and still, warmed gently by the flow of water. Through one opening, alkaline fluid enters, carrying hydrogen and carbon-rich molecules. Through another, the colder ocean presses in with its own mixture of minerals. Where the two waters meet, chemistry awakens. Protons gather along the mineral walls, creating a quiet pressure that encourages reactions. Molecules caught in these spaces might rearrange themselves in ways that would be impossible in the open ocean. Some might form longer chains, others might take on new shapes that allow further transformation. These mineral pores acted like primitive cell walls. They offered boundaries without needing fragile membranes. They kept molecules close together, giving them time to interact. They shielded reactions from being swept away by currents and protected delicate structures from sudden destruction. In these tiny chambers, early metabolic cycles could take root, supported by the constant flow of energy from below the seafloor. The walls themselves added to the process. Iron and sulfur, woven into their surfaces, guided electrons gently from one molecule to another. Each movement created a small burst of energy, a spark that fed the growing chemical networks. The constant nature of the vents was essential. On the surface, pools rose and fell with the tides. They warmed in sunlight, then cooled in darkness. But in the deep sea, the vents offered stability. Their flows were steady, delivering ingredients day and night. Their temperatures changed slowly, allowing fragile molecules the chance to form and persist. Their internal chambers stayed sheltered, offering protection in a world where early chemistry was easily undone. The vents created an environment where progress, however small, could accumulate. They offered a foundation where early molecular steps could build upon one another. As protocells drifted through these regions, some might have settled near the vent structures. Their membranes, though fragile, gained strength from the steady nutrients that flowed around them. The gradients across their boundaries mirrored those of the vents themselves. Over time, the protocells that mimicked the energy systems of the vents found themselves more stable, able to support reactions within their membranes. These early partnerships between chemistry and environment helped shape the first quiet strategies of survival. The vents did more than provide ingredients. They offered a kind of scaffolding, a natural framework where energy and structure aligned. They helped create conditions where molecules could be held, transformed, and encouraged to repeat reactions. In their protective chambers, early metabolisms grew more complex, drawing strength from the gentle slopes of charged particles that flowed endlessly through the mineral walls. In the darkness of the deep ocean, where the world moved slowly and with steady grace, these vent systems became sanctuaries for the earliest forms of order. The planet, through its inner heat and ancient minerals, offered a place where chemistry could linger long enough to imagine the first steps toward life. While the deep ocean explored its own quiet experiments around mineral vents, another theater of chemistry played out high above, along the shifting borders where land met sea. Here, The tides moved with a gentle rhythm, rising to fill shallow basins carved by ancient waves, then retreating to reveal stones warmed by sunlight. These tidal pools, fragile and temporary, offered a very different kind of environment from the steady darkness below. They lived by cycles, and those cycles gave Earth new ways to weave complexity into the fabric of its early chemistry. Each time the tide advanced, it carried with it a mixture of molecules gathered from the wide ocean. Chains of amino acids, fragments of RNA, fatty acids, and smaller organic pieces drifted into the pools. They settled among grains of sand, lodged in cracks along the stone, or floated gently just beneath the surface. Then, as the water slowly withdrew, the pools began to shrink. Their edges tightened inward, leaving behind thin films of water that grew more concentrated with every passing moment. Molecules that had been free to drift now pressed close together, touching in ways the open ocean rarely allowed. During these drying phases, polymer formation became more likely. Without the constant motion of waves and the heavy dilution of deeper waters, molecules were encouraged to join into longer chains. Amino acids that had floated separately now linked into peptides, adding to the growing tapestry of chemical variety. Nucleotides found one another among the folds of drying sediment and sometimes connected into short strands of RNA. Fatty acids gathered in the narrowing pools and formed simple membranes that curled into small spheres. These formations were not directed by any guiding force. They arose because the environment created moments where closeness allowed new possibilities. When the sun reached its highest arcs, heat deepened the effect. Warmth coaxed water to evaporate, leaving molecules perched on stones like paint on an ancient canvas. Some reactions demanded this heat. Bonds that would never have formed in cold depths took shape in the soft flicker of sunlight warming the rocks. The air shimmered above the drying pools, and within that shimmering space, chemistry gained a looseness that let new structures appear. Sunlight carried energy that seeped into the molecules, helping them overcome barriers that would have been insurmountable in darkness. Yet these pools were not permanent. As the day drifted toward evening, the tide returned. Cool ocean water flowed across the stones once more, lifting the concentrated materials back into solution. Some chains dissolved, others remained intact, carried gently into the larger sea. A few protocells, formed during the drying hours, floated free and drifted toward new environments. With each cycle, the pools acted like small engines of creation. They built, released, then reset the stage. Over countless cycles, they produced a reservoir of molecules far more diverse and complex than anything the open ocean could maintain on its own. Sunlight also drove reactions that required a steady supply of energy. Certain organic molecules absorbed the light and changed their shapes as they did so. These new shapes carried possibilities for forming bonds that darkness alone could not encourage. The upper layers of water glowed faintly with this activity, especially in the shallower pools where sunlight touched every corner. These reactions were delicate. Too much light could break the molecules apart. Too little meant nothing new would happen. But in the soft balance of dawn and afternoon, the pools found a rhythm that supported gentle creation. Nature still preserves clues from this ancient process. Along modern coastlines, microbial mats grow where sunlight meets shallow water. They form layered structures, each layer supporting a different type of chemistry. The mats trap sediments, build small mounds, and create textured surfaces that ripple with patterns of life. Although these mats are living, their layered design offers a glimpse into how early chemistry may have arranged itself in the absence of cells. The mats concentrate organic materials, protect delicate reactions, and create microenvironments similar to the ancient tidal pools. They stand as quiet reminders of how structure and sunlight once worked together to guide early chemical steps. In certain parts of the world, these mats form stromatolites, rounded structures built through layer upon layer of trapped material. Their presence tells a story of shallow waters that encouraged organized systems long before complex life appeared. Although stromatolites belong to a later chapter in Earth's history, they echo a deeper past where natural layers nurtured chemical progress. In the tidal pools of the early Earth, this layering happened without living organisms. Evaporating water formed thin films where molecules arranged themselves along mineral grains. Returning tides pulled the arrangements apart, then rebuilt them in the next cycle. Over time, these layers guided reactions that created new chains, new shapes, and new arrangements of matter. The world was learning how to use cycles to build complexity, just as later life would use cycles to grow, divide, and adapt. As the oceans continued their gentle rise and fall, the pools remained patient teachers. They demonstrated that creation often begins in the quiet spaces between presence and absence, between water and air, between heat and coolness. Through these simple rhythms, Earth offered molecules a chance to gather, change, and take small steps toward the long arc that would one day lead to life. As Earth continued its slow transformation, quiet chemistry began to resemble something more than simple reactions. Molecules folded, gathered, and shaped themselves within sheltered spaces. Metabolisms found footholds near vents and in warm pools, and protocells drifted across calm waters. Still, the world remained without voices or motion visible to the naked eye. Whatever life was becoming, it did so softly, leaving only traces so faint that billions of years later they would feel more like whispers than declarations. Those whispers are what scientists look for today when they search the ancient rocks of Earth. In some of the oldest stones, pressed deep within ancient crust and later lifted toward the surface, tiny structures appear. They are small as grains of dust and fragile enough to crumble under the slightest pressure. Yet they hold shapes that resemble the outlines of early microbes. These microfossils, dated to more than 3.5 billion years ago, offer one of the earliest glimpses into what life may have looked like before it learned to grow complex. Their contours are simple, rounded, and often tubular, like the faint shadows of cells that once floated through warm seas. These microfossils do not speak clearly. Time has pressed them, heated them, and weathered them. Their original material has been replaced by minerals that settled in long after the organisms vanished. Some shapes formed through natural geological processes, leaving patterns that imitate life without involving any biology at all. Sorting the ancient living from the ancient accidental requires a gentle touch and careful patience. In many cases, a single structure cannot reveal enough. The rocks must be studied layer by layer, seeking patterns that repeat themselves across vast stretches of stone. Beyond shapes, scientists search for chemical signatures that hint at life's earliest breath. Carbon, the backbone of organic molecules, comes in different forms. Living organisms tend to use lighter carbon because it reacts more easily in the pathways that support life. When these organisms die and settle into sediments, they leave behind ratios of carbon that differ from those created by non-living processes. In some of Earth's oldest rocks, these carbon isotope signatures tilt toward patterns that suggest biological activity. They do not prove life's presence alone, but they add a soft layer of evidence that aligns with the idea of early cells quietly shaping their environment. Near ancient shorelines, another form of evidence appears in structures called stromatolites. These layered mounds rise from shallow waters, like gentle ripples frozen in place. Modern stromatolites are built by photosynthetic communities, where microbes grow in thin films that trap sediment, creating layers over time. When similar shapes appear in very old rocks, scientists see a hint that early life may have formed communities even before complex cells evolved. The ancient stromatolites lack the crisp detail of modern ones. They are blurred by age, smoothed by pressure, and changed by minerals that seeped into them during long burial. Still, their layered growth resembles the patterns created by living mats, suggesting that early microbes might have gathered in sunlit shallows, quietly using sunlight to build energy. Photosynthetic life at that time would not have resembled the bright plants we know now. Instead, it would have been slow, gentle, and often anoxygenic, meaning it did not yet release oxygen into the atmosphere. These ancient communities lived in places where sunlight could touch the water, but where the conditions remained calm enough for delicate films of microbes to hold their shape. Their presence implies that life had already learned to harness the sun, even if only in small ways, long before the great oxygen transformations that came later. Interpreting this early evidence is challenging. Rocks of such age have endured intense pressure and heat from within the earth. They have been stretched, folded, and cracked. Fluids have flowed through them, sometimes altering their chemistry entirely. Many structures that appear biological may have been sculpted by physical forces. Some carbon signatures could arise from high temperature reactions rather than living processes. Even stromatolite like shapes might form in rare cases without biology, created by simple sediment interactions guided by tides and minerals. To understand these ancient markers, scientists must consider the context of each stone. A single microfossil is not enough. A single carbon signature is not enough. The story emerges only when many lines of evidence support one another, forming a quiet chorus that suggests life was present. Even then, the conclusions remain gentle, never absolute. The early Earth kept its secrets well, and time has blurred the traces almost beyond recognition. Yet the fact that hints remain at all is remarkable. After billions of years of shifting continents, erupting volcanoes, and the slow rising and falling of seas, small shadows of early life still lie within the stone. They are faint, but they hint at communities that once spread across shallow waters, at cells that drifted through warm oceans, at metabolisms that shaped carbon before the atmosphere carried oxygen. They remind us that life began not with drama but with quiet persistence, leaving traces that only the patient eye can see. In these ancient rocks, Earth carries its first memory of living things, written softly in patterns that have survived the long passage of time. As the ancient Earth gathered its earliest traces of life, countless tiny experiments unfolded across oceans, pools, and mineral-rich landscapes. Many faded quietly, leaving no mark in stone. Others lingered long enough to shape small communities in warm shallows or near gentle vents. Out of this wide and varied tapestry, one lineage found a way to endure. It was not the first form of life, and certainly not the only one that arose in those early days, but it was the one that survived every shift the young planet placed before it. Today, we call it the last universal common ancestor, or Luca, a quiet presence from which all modern life descends. Luca was not a single perfect cell standing alone in the world. It was part of a small and changing population of early organisms, each one shaped by the environments that held them. Luca itself likely looked very simple to the eye, more like a tiny bubble of gel than anything we might recognize as a creature. It held no nucleus, no intricate internal structures, and no complex shapes. Yet within its thin membrane, it carried the features that would one day echo across every living being on Earth. Inside Luca, fragile strands of genetic material guided the assembly of basic proteins, each protein folded into shapes that supported its survival. These proteins helped manage reactions that allowed Luca to harvest energy from its surroundings. They formed parts of small molecular machines that all life today still relies on in some form. In this way, Luca was both humble and extraordinary. Its simplicity hid the seeds of the biological richness that would eventually fill the world. The metabolic pathways shared by all known life offer hints of what Luca's world was like. Modern organisms, whether they live in sunlit forests or deep underground, rely on reactions that move electrons from one molecule to another. These cycles support energy flow in cells and help build the molecules needed for growth. The unity of these pathways suggests that Luca used similar methods. It likely lived in an environment rich with hydrogen and minerals that could donate or accept electrons. Such conditions appear in places influenced by the Earth's deep interior, where warm water meets reactive stone. Luca also depended on enzymes that stitched together carbon compounds, forming the building blocks of proteins, nucleic acids, and lipids. These pathways remain nearly universal across life today, hinting at their ancient origins. They reveal a world where energy did not come from sunlight alone, but from the chemistry of the earth itself. Luca was shaped by a landscape that offered steady energy, allowing its cells to maintain the delicate balance needed for survival. It is important to remember that Luca was not the first organism to appear. Before it came many other forms, each exploring its own path toward stability. Some may have relied on metabolic cycles that differed from those Luca carried. Others may have formed in environments far from where Luca later thrived. The early Earth held room for many possibilities, but as the planet shifted, cooled, and faced periods of upheaval, only Luca's lineage endured. Its particular combination of pathways and genetic tools allowed it to survive conditions that erased other early lineages from history. The environment where Luca lived was likely sheltered. While the surface of the Earth experienced storms, temperature swings, and the constant push of tides, the deep ocean offered more gentle rhythms. Many scientists imagine Luca living near alkaline vents, where warm mineral-rich water flowed through porous rock. The chambers within these vent systems provided stability, shielding early cells from sudden changes. The natural gradients across mineral surfaces supplied energy that resembled the systems used by modern cells to produce fuel. In such places, Luca's ancestors could gather, divide, and persist without the disruptions that often break fragile membranes. These vent environments also carried metals like iron and nickel, which support the reactions that move electrons through metabolic pathways. The presence of these metals in essential modern enzymes hints that Luca lived in a world where such metals were abundant. The gentle warmth of the vent chambers, neither too hot nor too cold, created a setting where delicate molecular structures could fold and unfold safely. Over generations, Luca's lineage adapted to this landscape, refining its systems in ways that would eventually support more complex forms of life. While Luca shared much with later organisms, it also lacked many features we now take for granted. It could not store large amounts of energy. Its genetic material was simpler and less stable. Its membrane relied on chemistry that modern cells have replaced with more robust structures. Yet Luca had something rare: resilience. Its combination of metabolism, genetic machinery, and cellular boundary created a system that could replicate reliably. Even when conditions changed around it, Luca and its relatives had enough flexibility to survive. As Luca's descendants spread into new environments, the world slowly filled with diversity. Some lineages adapted to sunlight, others to darkness. Some learned to breathe oxygen long before the air held much of it. Others thrived in acidic pools or beneath layers of sediment. Despite their differences, they all carried the quiet signature of Luca in their cores, a reminder of the first lineage that found a lasting home on Earth. Through these shared features, Luca remains with us. Every heartbeat, every breath, every unfolding leaf and drifting microbe carries a trace of that ancient cell. The world changed around it countless times, yet its legacy stayed intact in the fabric of life that followed. As Earth's early organisms settled into their hidden corners of warm water and mineral-rich shelter, a quiet tension began to grow. Chemical networks had formed that could gather energy, fold into useful shapes, and build tiny structures. But none of these steps meant anything lasting unless one more threshold could be crossed. For life to spread, to adapt, to remember the successes of one moment and carry them into the next, it needed a way to make copies of itself. Without copying, every fragile achievement would dissolve back into the ocean, leaving no trace for the future. At the center of this story was RNA, the flexible molecule that had already proven its ability to store information and guide reactions inside early protocells. But although RNA could fold into helpful shapes, it faced a great challenge. Making a copy of an RNA strand required each nucleotide to find its partner and link itself into place. In the warm, shifting waters of early Earth, this was not easy. The strands could fall apart before they were finished. Bonds might form in the wrong order or not at all. Heat loosened the molecules, and water often broke the chains before they grew long enough to matter. Replication was possible in theory, yet elusive in practice. Still, within the chaos, small breakthroughs emerged. Some RNA strands folded into shapes that helped bring other nucleotides together. These folded strands acted like tools, holding pieces in place long enough for new bonds to form. Their curves and loops created pockets where copying could begin. These tools were ribozymes, RNA molecules that behaved like enzymes. They were not alive, but they offered guidance, shaping reactions that would otherwise drift without direction. The first ribozymes were simple. They might have copied only short sections of RNA or performed their work slowly. Their accuracy was low, and mistakes were common, but mistakes did not end their usefulness. In fact, the small changes introduced during copying sometimes created new ribozymes with slightly different shapes. A few of these shapes allowed the molecules to fold more firmly or link nucleotides more efficiently. Some could attach to the end of an RNA strand and extend it by a handful of nucleotides before drifting apart. Others helped stabilize weak bonds, protecting them from breaking in the presence of water. These early copying events were brief glimmers of continuity in a world where most molecules had no memory. When an RNA strand preserved part of its structure through replication, even if imperfectly, it carried a whisper from the past into the future. And if the copy supported useful reactions inside a protocell, the protocell was more likely to survive long enough to divide or to merge with another, sharing its growing set of molecular tools. As replication improved, another subtle change began to take shape. A strand that copied itself too poorly risked losing all structure within a few generations. A strand that copied itself too perfectly could not explore new forms. Somewhere between these two extremes lay a balance, a place where errors occurred slowly enough to preserve important functions, yet quickly enough to allow new possibilities to arise. Early ribozymes began to adopt shapes that favored this balance. They nudged nucleotides into place with slightly greater accuracy, reducing the most harmful mistakes while still allowing variety. This soft shift toward error correction did not involve intention. It emerged because protocells with slightly more reliable copies tended to remain intact longer. Their metabolisms worked more smoothly. Their membranes stayed stable. Their internal chemistry supported the formation of additional chains. Over countless cycles of replication and division, the ribozymes that introduced fewer harmful errors became more common. In this way, the first foundations of heredity took hold. With copying came something entirely new. Evolution began. Once RNA strands could replicate themselves, even imperfectly, they entered a world of variation and selection. Some strands folded into shapes that supported more efficient energy use. Some improved the strength of protocell membranes. Some helped guide reactions that produced essential molecules. Those strands lingered, spreading through protocell communities and gradually shaping the chemistry of early life. The earliest forms of evolution were quiet, unfolding slowly in the hidden pockets of the young ocean. There were no eyes to witness them, no movements visible to the surface waters above. But within the sheltered spaces where protocells drifted and settled, copying allowed change to accumulate. Each new strand carried echoes of its ancestors, with small differences that shaped its fate. Some versions persisted, others faded. Over time, the threads that survived wove themselves into increasingly stable systems. Eventually, these systems would support the development of DNA, proteins, and the complex machinery that fills modern cells. But long before those intricate histories began, the world was shaped by this first humble act: the ability of molecules to create imperfect copies of themselves. Copying gave the early Earth a sense of continuity. It allowed information to stay in the world instead of vanishing with each tide. In those fragile protocells, drifting through ancient seas, the quiet rhythm of replication became the heartbeat that carried life forward. As early life continued its slow shaping within the quiet corners of ancient oceans, the world entered a new stage of chemical refinement. RNA had carried life through its first uncertain steps. It folded into helpful shapes, guided reactions, and learned to copy itself with growing steadiness. But as protocells grew more complex and their internal chemistry deepened, RNA's strengths began to reveal their limits. It was a molecule of many talents, yet it struggled to be both the keeper of memory and the tool that shaped daily reactions. In those soft, ancient waters, evolution began to carve a new path, one that would divide the responsibilities of life into clearer roles. The first shift came with the emergence of DNA, a molecule shaped with a patience and sturdiness that RNA could not easily match. DNA carried a calmness in its structure, a double helix that wrapped information in gentle layers of protection. Its shape resisted damage from heat and reactive chemicals more effectively than RNA's single strands. Where RNA bent and twisted with ease, DNA held its form steady, preserving its message through changes that would have unraveled other molecules. This stability made DNA a more reliable storehouse for genetic information, especially as protocells began to rely on longer and more complex sequences to support their survival. RNA did not disappear with the rise of DNA. Instead, it shifted into a new role, one that honored its flexibility. While DNA stored the instructions, RNA acted as the messenger. It carried small pieces of information from DNA's protected chambers into places where new molecules needed to be built. Its freedom to fold allowed it to interact with many different partners, guiding the assembly of proteins with careful precision. RNA became the voice that read DNA's script and delivered it to the machinery of the cell. Proteins, in turn, rose to become the dominant actors in the cell's inner world. They were crafted from chains of amino acids, each chain folding into intricate shapes that performed tasks RNA could manage only faintly. Some proteins acted like scissors, cutting molecules apart. Others behaved like tiny hinges or levers, moving atoms from one place to another. Some formed tunnels that allowed nutrients to enter the cell, while others strengthened membranes or supported delicate structures. Their diversity was immense, shaped by the near endless ways amino acids could combine and fold. The transition toward a system ruled by DNA, RNA, and proteins did not happen suddenly. It unfolded through countless generations of early organisms, each small change offering a slight advantage. A protocell with more stable genetic material could preserve useful traits more easily. A protocell that relied on proteins for catalyzing reactions could build structures and harvest energy more efficiently. Gradually, cells that kept DNA safe within their boundaries and used RNA as a relay began to thrive in environments that challenged older, simpler systems. The separation of roles became one of life's most elegant innovations. DNA stored the instructions with great care. RNA read and delivered those instructions with flexibility. Proteins carried out the work with strength and precision. Each molecule type supported the others, creating a triangle of cooperation that remains at the heart of every cell on Earth. This cooperation allowed early life to move past the fragile experiments of its beginnings and into a stage where complexity could grow without collapsing under its own weight. There were evolutionary advantages to this division, subtle at first but profound over time. DNA's stability meant that beneficial traits could last through many cycles of cell division, creating a foundation for long-term adaptation. RNA's versatility allowed rapid changes in how the cell responded to its environment. Proteins offered specialized capabilities that made metabolism more efficient and membranes more resilient. Together, these roles created a system where information, communication, and action were balanced in a way that supported the growth of more advanced organisms. As these early cells drifted through the oceans, their chemistry began to organize itself into networks that could withstand the unpredictable shifts of the ancient world. Proteins refined the cycles that produced energy. RNA guided the creation of those proteins with increasing accuracy. DNA held the memory of every successful adaptation. Over time, cells became less vulnerable to chance. They could repair damage, correct small errors, and maintain stable environments within their membranes. With the rise of DNA and proteins, life gained a deeper sense of continuity. It could build upon its past. It could inherit the successes of countless ancestors. The world that once held only fleeting chains and fragile protocells now carried cells with the capacity to grow, divide, and spread across new landscapes. In these early chapters, Earth's story shifted from a world shaped by chemistry alone to one shaped by living systems that could endure. The gentle partnership between DNA, RNA, and proteins became the quiet architecture of life, a framework that still guides every organism today. Through their shared roles, life found a way to preserve its memory, express its needs, and act upon its environment with increasing grace. As early cells refined their inner chemistry and learned to hold their genetic memories with greater care, the oceans began to shimmer with possibilities that had not existed before. Life had found ways to gather energy from minerals, from gentle heat, and from the quiet flow of electrons across its membranes. Yet, the greatest source of energy on the planet still streamed down from above, touching the surface of the sea with soft golden light. For millions of years, this light passed through the waters unused, a silent invitation waiting for life to discover it. In time, Certain microbes drifting near the surface learned to respond to that invitation. Their membranes housed pigments, delicate molecules that absorbed sunlight in small bursts. These pigments did not create oxygen as modern plants and cyanobacteria do. Instead, they powered a form of anoxygenic photosynthesis, a process that used light to move electrons but relied on other compounds, such as sulfur or iron, instead of water. The oldest photosynthesizers lived in gentle shallows, where sunlight reached easily yet where conditions remained quiet enough for fragile cells to thrive. They did not brighten the world with oxygen or transform the sky. They simply learned to turn sunlight into energy in a way that supported their steady growth. The pigments in these early microbes likely glowed faintly when struck by sunlight, their colors deepened by the warmth of the sea. As the pigments absorbed energy, they passed electrons along carefully arranged chains within the cell. This flow supported the building of sugars and other molecules the cell needed to survive. The process was simple compared to what later life would develop, but it marked a profound shift in Earth's story. For the first time, life tapped directly into the energy of the sun, instead of relying entirely on the reactions born from Earth's interior. These anoxygenic photosynthesizers formed communities that drifted with the tides. Some clung to mineral grains, others settled into thin films along sheltered coasts. Over time, their presence created new ecosystems. In places where sunlight remained steady, clusters of photosynthetic microbes grew thick enough to shape the environment around them. They consumed available nutrients, altered local chemistry, and created patches of life that could support organisms relying on the molecules they produced. This slow buildup of sunlight-powered communities added a new layer of complexity to Earth's biosphere, a layer that spread gently across bright waters and into regions once occupied only by drifting organics. With the rise of photosynthesis, surfaces near the ocean's top layers became more dynamic. The day brought a pulse of activity as the microbes absorbed light and produced energy. Night brought quiet when the microbes relied on stored molecules or shifted to alternate sources of energy. These rhythms formed the earliest daily cycles of life, driven directly by sunlight. Over long stretches of time, such cycles supported the creation of new metabolic pathways, allowing life to diversify further. The ecosystems shaped by these early microbes were subtle but persistent. In shallower pools, the photosynthesizers trapped sediment and created thin layers that slowly built upon one another. These layers served as gentle footholds for other microbes, which used the organic molecules produced during periods of sunlight. The communities resembled a kind of early tapestry, woven from cells that exchanged resources without forming complex partnerships. Even in their simplicity, these groupings represented a step toward the structured environments that would one day fill shorelines and lake beds around the world. The true transformation brought by photosynthesis came not from the first pigments, but from the possibilities they unlocked. With sunlight as a dependable energy source, life could expand into regions previously too poor in chemical energy. Cells no longer had to depend solely on vents, minerals, or rare molecules drifting through water. The sun provided a broad, gentle stream of power across the entire surface of the planet. This widespread availability allowed life to grow in abundance. The seas that had once held scattered protocells and isolated lineages began to host dense microbial films that covered stones, drifted through currents, and formed small floating clusters. Although these early forms of photosynthesis did not release oxygen, they laid the groundwork for the evolution of organisms that would. The ability to absorb sunlight and convert it into chemical energy proved so useful that nature refined and expanded it through countless generations. Eventually, the tools of anoxygenic photosynthesis were reshaped into the machinery of oxygenic photosynthesis, a process that split water and released oxygen into the air. The transition would come later, with cyanobacteria, and would change the planet forever. But even before that great transformation, the early photosynthesizers quietly reshaped Earth in ways that made future innovations possible. Their influence touched the atmosphere, the chemistry of surface waters, and the structure of ancient ecosystems. By anchoring life more firmly to the sun, they allowed the biosphere to grow in scale and resilience. The world became richer in organic molecules and more varied in the niches available to young organisms seeking new ways to survive. In the gentle light of early mornings, long before oxygen filled the sky, these first photosynthetic cells drifted through calm waters. Their pigments captured the glow of the sun, and their reactions supported communities that softened the edges of a once barren world. Through their quiet work, they set Earth on the path toward the vibrant and oxygen-rich planet it would one day become. As the first photosynthesizers drifted through the ancient seas, quietly absorbing sunlight without altering the sky, Earth continued its slow and patient transformation. The early pigments that captured sunlight had opened a doorway into a new kind of energy, yet the world still breathed the chemical air of its earliest days. Life relied on minerals, hydrogen, sulfur, and simple sunlight-based pathways. The atmosphere above remained gentle in composition, untouched by oxygen, but in the calm shallows of young coastlines, a new lineage of microbes began to shape a future neither the seas nor the sky had ever known. These microbes, now called cyanobacteria, carried pigments more sophisticated than any that had come before. Their molecules could pull electrons directly from water, a resource spread across the entire surface of the planet. This process, known as oxygenic photosynthesis, allowed them to capture vast amounts of solar energy. When they split water to harvest its electrons and hydrogen, they released oxygen as a byproduct. At first, the small amounts of oxygen drifted into the surrounding water, where it quickly reacted with dissolved minerals such as iron. The oxygen vanished almost as soon as it appeared, swallowed by the chemistry of the oceans. But cyanobacteria multiplied and spread, forming long, silky mats that covered rocks and shelves in warm, sunlit bays. With each pulse of sunlight, they exhaled more oxygen into the sea. For a long time, oxygen remained invisible in the atmosphere. It reacted with everything it touched, and Earth, still rich with easily oxidized minerals, absorbed it. But the cyanobacteria did not slow their gentle production. Day after day, they filled the waters with oxygen faster than the oceans could consume it. At last, after uncounted generations, the balance shifted. The surface waters became saturated. Bubbles of oxygen formed in the shallows. Some oxygen escaped into the air above, entering an atmosphere that had never held such a gas in meaningful amounts. To early life, this oxygen was not a gift, it was a threat. Oxygen is highly reactive, eager to bind and break apart molecules that had supported living reactions for millions of years. The metabolic pathways that guided ancient microbes were not built to withstand it. For many organisms, oxygen damaged their structures as surely as heat or acid. Entire communities that had thrived in environments of gentle chemical stability now faced a rising tide of a gas that disrupted their delicate balance. Some species retreated into deeper waters. Others found refuge in sediments or in places where oxygen could not penetrate. Many vanished completely, lost in a transformation that swept across the planet with quiet persistence. Yet even as oxygen reshaped the biosphere, it also opened doors that had been closed since the beginning of life. When oxygen rose into the upper layers of the atmosphere, Sunlight transformed it into ozone, a gas that settled into a thin but powerful protective layer high above the Earth. Before ozone formed, harmful ultraviolet radiation poured freely onto the surface, limiting the environments where life could safely grow. With ozone in place, the world gained a shield. Sunlight reaching the surface became softer, allowing new habitats to open across coastlines and shallow seas. Oxygen also changed the chemistry of the oceans. Iron that once drifted freely in the water combined with oxygen to form solid minerals, settling to the seafloor in great rust-colored layers. These formations, preserved in ancient rocks, record the moment when oxygen first saturated the seas. As iron settled out, the oceans became clearer, allowing sunlight to reach deeper regions. This clarity gave cyanobacteria more room to expand their communities. The increased light also created conditions for new forms of photosynthesis to develop in microbes that had been limited to dimmer environments. In the long term, oxygen became a foundation for powerful metabolisms. Cells that learned to use oxygen directly gained access to energy far greater than what earlier pathways could offer. This opened a path toward larger, more complex life forms. Over millions of years, oxygen-breathing organisms emerged, building internal structures that took advantage of oxygen's energetic potential. The rise of eukaryotic cells, with their internal compartments and specialized machinery, depended on this shift. Without oxygen, such complexity would have been difficult, perhaps impossible. The oxygen revolution did not happen quickly. It unfolded through gentle rhythms of growth and decline. Cyanobacteria thrived, produced oxygen, and changed the world around them. Life adapted or faded. The atmosphere climbed slowly toward new compositions. Over time, oxygen spread across the planet and into its deepest corners. By the time the sky reached its stable levels, the Earth had become a different place. The atmosphere shimmered with a subtle blue tint. The oceans glowed with new clarity. The land, once barren and hostile, became a place where life could one day take root. All of this began with simple microbes floating in shallow seas, carrying pigments that caught sunlight in ways never seen before. Through their quiet work, they transformed the chemistry of the planet, shaped the course of evolution, and prepared the world for the rich diversity of life that would follow. As oxygen slowly entered the oceans and the sky, the world began to change in ways that touched every emerging organism. The calm chemical environments that once sheltered life grew more dynamic. Sunlight brightened the shallow waters as iron settled from the sea. Temperature shifts became more dramatic in open areas exposed to day and night. Volcanic landscapes continued to release heat and gases, shaping tides and currents. All across the planet, life met challenges that tested the fragile systems it had built through countless generations. Even before oxygen rose in the atmosphere, early microbes had already lived under conditions that pushed their chemistry to its limits. Ultraviolet radiation reached the surface with little obstruction. The young ozone layer was barely forming, offering only the faintest protection. Cells floating near the top of the water absorbed sunlight that was both life-giving and destructive. When ultraviolet rays struck DNA or RNA, they twisted bonds and broke strands, threatening the instructions that guided every process inside the cell. For organisms dependent on accurate copying, this radiation posed a constant danger. Heat also shaped early life. In many environments, temperatures shifted by wide margins over short distances. Near volcanic regions, the water could warm quickly, bathing cells in heat that loosened their proteins and destabilized their membranes. Farther away, cooler waters could slow essential reactions, making it difficult for cells to maintain the rhythms of metabolism. These fluctuations forced life to become flexible. Organisms that could adjust to variations in heat gained an advantage over those restricted to narrow temperature bands. Acidity presented another challenge. In places where volcanic gases dissolved into the oceans, the water grew acidic enough to interfere with chemical reactions inside cells. Acids broke down bonds, altered protein shapes, and made it difficult for membranes to retain their structure. Microbes that found themselves in these regions needed strategies to keep their inner chemistry stable despite the shifting environment outside. Against this backdrop of stress, life began to develop subtle systems that offered protection. One of the most important was the ability to repair damaged DNA. Even the simplest cells carried small proteins that could recognize when a strand of DNA had been broken or altered by ultraviolet light. These proteins worked with quiet precision, sliding along the DNA and correcting mismatched bases or stitching broken strands back together. Though primitive, these DNA repair mechanisms helped cells maintain their genetic memory across generations. With each improvement, cells became more resilient, better able to survive in bright, shifting waters. Temperature stress brought another innovation. When heat threatened to unfold the proteins inside a cell, special molecules known as heat shock proteins stepped in. They acted as caretakers, helping damaged proteins refold into their proper shapes. When the temperature dropped again, these proteins continued to stabilize the cell's internal structures. This ability to protect and restore essential components gave cells greater freedom. They could survive near thermal vents, in sun-warmed shallows, or in regions where volcanic activity created sudden instabilities. Over time, microbes expanded their stress response systems. Some developed proteins that shielded DNA from reactive chemicals. Others built enzymes that controlled acidity within their membranes, ensuring the cell's interior stayed balanced even when the environment around them changed. Some learned to sense danger, activating protective pathways when heat or radiation increased. These systems grew gradually, shaped by the pressures of each new challenge. No single cell planned these transformations. They emerged from the quiet cycles of mutation and survival, where those with stronger defenses simply lasted longer. The accumulation of these responses accelerated innovation. Cells with DNA repair remained stable enough to explore new genetic combinations. Cells protected by heat shock proteins endured conditions that opened access to richer environments. Stress created openings for new metabolisms, new pigments, and new forms of photosynthesis. It pushed life into corners of the world that once seemed unreachable. In these corners, new adaptations took root. The rise of oxygen introduced fresh stress. Oxygen reacted with countless molecules inside cells, generating reactive byproducts that damaged proteins, membranes, and DNA. But instead of ending life's progress, this challenge encouraged new innovations. Some organisms developed enzymes that neutralized reactive oxygen, transforming it into harmless molecules. Others learned to use oxygen directly, gaining access to powerful energy, releasing reactions that allowed for even greater growth and complexity. What began as a toxin gradually became one of the most valuable resources on the planet. Stress shaped the membranes of cells as well. Organisms developed stronger lipid layers that resisted heat, acidity, or reactive chemicals. Some created additional barriers or compartments within their cells, separating delicate processes from harsh environments. These internal structures laid foundations for more advanced forms of life, allowing reactions to occur in specialized regions with greater control. Across oceans, lakes, and volcanic plains, early life adapted not by resisting change, but by learning from it. Each challenge offered an opportunity for refinement. Each risk encouraged new pathways and tools. Life did not move through this era as a fragile flame sheltered from the world. Instead, it grew through the world's challenges, shaping itself in response to the forces that pressed upon it. In this long and patient dance with stress, life gained strength and resilience. The world's early dangers became the very pressures that guided evolution, helping cells discover new ways to endure, to grow, and to take their next quiet steps into a changing planet. As early life continued to adapt to shifting light, rising oxygen, and the deep pressures of an ever changing world, another set of partners worked quietly in the background. These partners were neither alive nor capable of change in the way cells were, yet they shaped every stage of early metabolism. They were minerals and metals, steady foundations beneath the oceans and within the crust, guiding the flow of molecules long before cells learned to guide themselves. In the warm waters that surrounded hydrothermal vents and mineral-rich shorelines, metals such as iron, nickel, and sulfur moved through the currents like silent helpers. Iron, abundant in the early oceans, carried electrons along its surface with ease. When molecules contacted iron-rich minerals, reactions that required electron flow became possible. This allowed simple chemical networks to arise, where electrons hopped from one molecule to another in patterns that resembled early metabolism. These reactions were not yet controlled by enzymes or shaped by genetic memory. They followed the laws of chemistry alone, unfolding across mineral surfaces that offered both structure and stability. Nickel played a similar role. It appeared in minerals around vent systems and within pockets of warm stone, where it helped drive reactions that transformed carbon dioxide into useful organic molecules. In time, nickel would become part of some of life's oldest enzymes, supporting reactions essential to the cells that descended from this ancient chemistry. But before enzymes existed, nickel's surface alone was enough to encourage the assembly of molecules that provided the raw material for early metabolisms. Sulfur offered yet another kind of support. In its various forms, sulfur could gain and lose electrons easily, creating cycles of energy exchange that resembled what cells would later adopt. Microbes that lived in early oceans eventually learned to rely on sulfur-rich reactions. But at the beginning, sulfur's chemical flexibility helped shape the environment itself. Sulfur-bearing minerals created gradients, pockets of reactive water, and surfaces where chemical chains could assemble. These gradients supplied energy in patterns similar to the ones cells still use today. Mineral surfaces played a central role in the assembly of early molecules. In the open ocean, organic compounds tended to disperse. They drifted apart, diluted by the vastness of the water. But on mineral surfaces, these same molecules gathered in dense layers, cracks in stone, folds in clay, and tiny ridges in metal-rich sediments created sheltered places where molecules could rest close together. When amino acids or nucleotides settled on these surfaces, they aligned in ways that encouraged bonds to form. The surfaces stabilized the molecules, holding them in place long enough for larger structures to emerge. Clays, in particular, offered a special kind of support. Their layered surfaces trapped water and organic compounds in thin films, creating gentle cycles of wetness and dryness similar to those found in tidal pools. As water evaporated, molecules on the clay grew more concentrated. As water returned, new layers formed. This steady cycle encouraged the growth of chains, such as RNA strands and short peptides. The clays acted like natural scaffolds, allowing early chemistry to grow in complexity. Catalysis, the process by which reactions occur more easily in the presence of certain materials became a quiet force behind these early steps. Minerals containing iron or nickel accelerated reactions that might otherwise take thousands of years. Their surfaces lowered the energy needed for bonds to form or break, guiding reactions along paths that supported the emergence of stable networks. This natural catalysis was the backbone of early chemical cycles. It created ordered flows of energy from hydrogen to carbon compounds, from sulfur to other molecules, and from one mineral surface to another. These cycles did more than sustain early chemistry. They gave life the patterns it would later adopt and refine. Modern cells still use iron in their metabolic pathways. They still rely on nickel-containing enzymes to process carbon dioxide. They still use sulfur in reactions that mirror the ancient exchanges once supported by minerals alone. The echoes of early geology linger in every breath taken by modern organisms, in every cell that moves electrons through its inner pathways. Because minerals and metals shaped the earliest forms of metabolism, geology and biology remain inseparable in origins research. The landscape itself provided the structure, the energy, and the stability that protocells needed to arise. The ocean floor offered gradients of heat and chemistry that nurtured early metabolisms. Rocks sheltered molecules from destructive forces and allowed them to assemble into increasingly complex arrangements. Without these geological foundations, life would not have found the guidance it needed to move from scattered molecules to organized systems. Even today, scientists study ancient rocks to understand life's beginnings. Within these stones, traces of early reactions remain. Iron-rich layers speak of oceans once filled with dissolved metals. Sulfur deposits reveal the cycles that shaped early metabolisms. Mineral patterns record the movement of water, heat, and chemistry long before organisms learned to shape their own environments. As life continued its slow journey toward greater complexity, the influence of minerals did not disappear. Instead, it became part of life's inner machinery. The earliest cells carried within them the memory of the stones that once guided their reactions. The earth itself had been both cradle and teacher. In those ancient waters, where minerals shimmered softly beneath drifting microbial mats, the partnership between stone and cell quietly unfolded, stitching geology and biology into one continuous story. Long before Earth held forests, reefs, or even the simplest animals, the oceans were filled with cells so small and delicate that they seemed like drifting sparks of chemistry rather than living beings. These early cells carried the basic machinery that life required, but little more. They held strands of genetic material, a scattering of proteins, and membranes thin enough to shift with the touch of a current. Their world was governed by simple reactions. Their needs were few. Their structures were plain, shaped only by the chemistry that helped bring them into existence. Early cells were simple because simplicity was enough. The young Earth offered steady thermal gradients, mineral-rich surfaces, and expanding sunlight-powered ecosystems. With these resources around them, cells needed only the most essential tools to grow and divide. Their membranes acted as barriers that held their chemistry together. Their enzymes guided reactions that supplied energy and rebuilt damaged parts. Their RNA and DNA stored the quiet instructions that allowed them to survive. In this early era, complexity was not yet required. Stability, more than sophistication, allowed cells to thrive. Yet even within these simple forms, the seeds of greater complexity began to take shape. As oxygen increased in the oceans and new pressures shaped microbial communities, cells faced challenges that required more nuanced control over their inner spaces. Reactions that had once unfolded freely now interfered with one another. Some processes produced harmful byproducts. Others required delicate conditions to succeed. The need for order emerged gently, pushed forward by the shifting chemistry of the world outside. From these pressures arose the earliest internal compartments. They were not yet true organelles, nor the elaborate structures found in modern eukaryotic cells. Instead, they were soft pockets within the cytoplasm where certain reactions could occur in relative isolation. Fatty molecules gathered into small folds and vesicles, forming bubbles inside the larger cell. These microenvironments allowed enzymes to work without interference, creating miniature laboratories for specialized tasks. Some compartments helped store energy-rich molecules. Others, concentrated reactants that would have been too diluted in the rest of the cell. These early divisions of space represented an important step. They allowed cells to separate conflicting reactions, protect delicate processes, and slowly refine their metabolic networks. Over countless generations, small improvements in the stability or structure of these compartments offered advantages. Cells that maintained orderly spaces inside themselves could adapt to wider ranges of conditions. They could handle oxygen's growing presence, process nutrients more efficiently, and preserve fragile molecules that would otherwise break apart. Alongside internal compartments, membranes themselves began to diversify. Early membranes had been simple sheets formed from fatty acids, flexible but vulnerable. As cells encountered heat, acidity, and reactive molecules, they experimented with new lipids. Some membranes became sturdier, composed of tighter molecular arrangements that resisted damage. Others grew more dynamic, able to change shape or divide with greater ease. Over time, certain microbes developed outer layers with different compositions than their inner membranes, creating multiple boundaries that offered control and protection. Membrane specialization also supported new methods of interaction with the environment. Channels and transport proteins embedded themselves within the membranes, guiding nutrients inward and waste outward. Some cells developed structures that allowed them to anchor themselves to minerals or move gently through the water. These innovations remained subtle in form, but they expanded the ways life could inhabit the world. Within these changing cells, cooperation among molecules became increasingly vital. Proteins interacted with one another to form small complexes, sharing tasks that no single molecule could manage alone. Chains of enzymes assembled into pathways, passing intermediates from one to the next in smooth succession. DNA and RNA refined their relationship, coordinating the storage and expression of genetic information with greater precision. Lipids, proteins, and genetic material learned to operate as integrated networks rather than isolated parts. This molecular cooperation laid the groundwork for more intricate systems. Some proteins stabilized DNA during stressful periods. Others guided the folding of fragile enzymes. Still others arranged themselves along membranes to form rudimentary scaffolds. Each new cooperative bond created opportunities for cells to explore different shapes, behaviors, or habitats. As these early patterns grew more established, life entered a slow turning point. Simplicity was no longer the only path to survival. Complexity offered advantages in an increasingly varied world. Cells with compartments could isolate dangerous reactions and develop new metabolic strategies. Cells with specialized membranes could survive in environments once too harsh to inhabit. Cells with cooperative molecular networks could experiment with new chemical solutions. Through millions upon millions of quiet generations, this gradual layering of complexity shaped the foundation of modern biology. The earliest hints of internal organization allowed cells to prepare for the more dramatic transformations that lay far ahead, including the rise of eukaryotes and multicellular life. But in this ancient chapter, the story remained soft and steady. Life explored new depths of structure, not through sudden leaps, but through countless small adjustments, each one preserving a successful insight gained from the world around it. In these gentle steps, Earth's simple cells began their long journey toward complexity, weaving order from the quiet dance of molecules within their tiny boundaries. As Earth's cells slowly grew in complexity, the oceans began to paint new patterns across their surfaces. Gone were the days when life drifted only as single specks, scattered through vast waters with little interaction. The rise of photosynthesis, the refining of metabolisms, and the strengthening of membranes allowed cells to gather in places where sunlight warmed the shallows and minerals shimmered near the coasts. These gentle environments became the first true ecosystems, built not from animals or plants, but from countless layers of microbes arranged like living tapestries beneath the waves. In the warm, shallow seas of the ancient earth, microbial mats spread across rocks and sediments in wide, soft carpets. These mats were built from many species, each forming a thin layer that supported the next. Cyanobacteria sat near the top, touching the sunlight that filtered through the water. Beneath them lived microbes that fed on the molecules produced above, and below those lived species that thrived on even smaller fragments, working in the dimmer shadows. Together, these layers formed structures that rose and fell with the tides, bending slightly as currents passed over them. The mats felt smooth beneath the water, yet were woven from millions of tiny cells. Some threads produced sugars from sunlight, others breathed sulfur or iron, some consumed waste products that would have been harmful if left to accumulate. Each layer depended on the others, not through intention, but through quiet exchanges shaped by their chemistries and needs. This interdependence allowed the mats to spread across vast stretches of seafloor, forming networks that changed the environments around them. At the heart of these early ecosystems lay a remarkable form of chemical recycling. When one species produced a molecule as part of its metabolism, another species used it as food or as a building block for its own processes. Cyanobacteria produced oxygen and organic matter. Some microbes used the organic matter to grow, releasing carbon dioxide that fed the photosynthesizers above. Others used the limited oxygen in small pockets, creating reactions that produced nutrients absorbed by deeper layers. Even the remains of dead cells became part of the cycle, broken down by microbes that specialized in reclaiming their molecules. This recycling created gentle flows of matter that looped endlessly through the mats. Every molecule had a journey. It might be born in a photosynthetic reaction, drift into the layer below, be pulled apart by another microbe, turned into new fragments, and then rise again as nourishment for different species. Nothing was wasted. Nothing moved without shaping something else. The mats were efficient not because they planned to be, but because evolution had sculpted their interactions so carefully over millions of years. Energy, too, flowed through these early ecosystems in a steady rhythm. Sunlight entered the system at the surface, captured by pigments that turned it into chemical potential. From there, energy trickled downward as cells consumed, shared, and transformed nutrients. Even in places where sunlight never reached, vents and mineral surfaces provided their own energy sources. Some mats formed near these warm places, blending sunlight-based and mineral-based metabolisms into a single community. Energy always moved from a source to many destinations, spreading through the layers like warmth moving through cloth. The pre-animal world was a place where energy traveled slowly and predictably. There were no predators to disrupt the balance, no sudden upheavals caused by large creatures consuming entire communities in a moment. Instead, the flow of energy resembled the turning of a tide or the shifting of dust in a quiet breeze, subtle, steady, and continuous. Microbes grew, divided, and recycled molecules in patterns that changed only over long stretches of time. This gentle predictability made early ecosystems remarkably stable. For millions of years, the mats persisted with little structural change. They expanded when conditions were favorable and shrank when waters cooled or chemical supplies shifted, but the overall design of their communities remained constant. Stability came from their layered nature. If one species struggled during a period of reduced sunlight or increased acidity, another species often filled its role temporarily. If oxygen rose too high in one part of the mat, deeper layers protected species that were sensitive to it. The mats carried built-in resilience simply through their diversity and their closeness to one another. Another reason for their stability lay in the absence of complex organisms. Without multicellular creatures reshaping their environment through movement, grazing, or competition, microbial ecosystems experienced few direct disturbances. Their greatest challenges came from geological changes, like shifting coastlines or volcanic events. When such changes occurred, fragments of mats could drift to nearby areas and re-establish themselves. Their simplicity made them adaptable. Their organization made them durable. As the ancient Earth continued to evolve, these microbial mats transformed the world around them. They produced oxygen that slowly gathered in the atmosphere. They trapped sediments that built structures still visible in some of the planet's oldest rocks. They created habitats for other microbes that would one day pave the way for more complex life. For a long time, they were the dominant force shaping the surface of the Earth. In these early ecosystems, the planet found its first breath of order. Life arranged itself not in isolation, but in communities of countless tiny parts, each thread woven into a fabric that covered the shallows of a quiet and growing world. The early Earth, even as it nurtured growing ecosystems, remained a world of restless forces. Its crust shifted often. Volcanoes vented heat and minerals into the sea, and far above, the sky carried remnants of the solar system's birth, drifting silently until gravity drew them inward. At times, these wandering stones struck the planet with such intensity that the surface was scoured clean, leaving little behind but molten rock and rising clouds of dust. These global catastrophes arrived without warning, interrupting the gentle rhythms that microbial communities had built over millions of years. Many of these impacts were powerful enough to sterilize Earth's surface. The heat they released boiled shallow waters, melted coastlines, and filled the atmosphere with debris that blocked sunlight for long stretches of time. The microbial mats that had once covered wide areas of the seafloor vanished in moments. Photosynthesizers lost their light. Delicate cells near the surface, already sensitive to radiation and heat, had little chance to survive in the aftermath. For a world that had only recently begun to stabilize its ecosystems, these cataclysms seemed to undo everything life had patiently crafted. Yet life endured. Even during the largest impacts, the Earth was vast enough to offer refuge. Deep underwater, temperatures changed more slowly. Heat from the surface cooled as it descended through the layers of the ocean. In these sheltered depths, microbes continued their quiet work. Some lived near hydrothermal vents, drawing energy from chemical gradients instead of sunlight. Others sheltered within sediments that insulated them from temperature spikes. These communities survived even when the surface turned hostile and the shallow seas briefly fell silent. Underground, life also found refuge. Microbes nestled into cracks within the crust, living in films of water trapped between stones. These pockets offered protection from heat and radiation. They held steady temperatures and supplied minerals that supported metabolism. In many ways, these underground microhabitats resembled small worlds of their own. They allowed life to retreat when the rest of the planet became unstable. As the surface cooled and the dust cleared, these hidden survivors slowly returned. Microbes from the depths drifted upward, carried by currents or by flows of mineral-rich water rising through vents. Cells sheltered within sediments spread across new coastlines as the seas settled. The recolonization of the planet was not quick. It happened gradually, like a slow breath returning to a patient who had been holding still for too long. But each time, life reclaimed the empty spaces with determination shaped by its long history. These repeated catastrophes did more than reset the planet's ecosystems. They shaped the very nature of life's resilience. Cells that survived intense heat or radiation passed on traits that improved their stability. DNA repair systems grew stronger in response to the damage caused by cosmic impacts. Membranes became more robust, better able to withstand sudden shifts in temperature or acidity. Proteins involved in stress responses refined their roles, offering cells new ways to endure the unpredictable forces of the world. Catastrophes also encouraged diversity. When ecosystems collapsed, survivors entered an environment free of competition. New niches opened. Mutations that once mattered little became important. Populations spread into places they had never occupied before. Over millions of years, these cycles of destruction and renewal allowed life to explore many possible paths, guided by both chance and the chemistry of survival. The global resets created by asteroid impacts shaped not only resilience but adaptability. Microbes that had once lived only in sheltered environments became pioneers of freshly cooled coastlines. Some learned to tolerate oxygen, which had been rising slowly in the atmosphere. Others formed new partnerships, exchanging nutrients or forming layered communities that supported more complex interactions. Each recolonization left a slightly different world behind, one where life carried a deeper memory of how to survive the next upheaval. As impacts became less frequent over time, the Earth settled into calmer rhythms. But the lessons from this tumultuous era remained embedded in the genes of all living organisms. The ability to repair DNA, to manage stress, to endure sudden change, and to recolonize empty spaces did not arise from quiet periods alone. These abilities were shaped during the times when the world was at its harshest. In the deep quiet after each catastrophe, when the planet's surface cooled and the oceans regained their clarity, life returned in forms both familiar and subtly changed. Microbial mats rebuilt themselves. Photosynthesizers rose once more toward the sunlight. The cycle of nutrients resumed its gentle flow. From devastation came renewal, and from renewal came innovation. Through these ancient resets, life learned not only how to endure but how to persist with greater strength. The early Earth tested its smallest inhabitants again and again, and in surviving, they forged the resilience that would support every future branch of the tree of life. After the early Earth endured its long seasons of fire, bombardment, and quiet cooling, the planet entered a moment of unexpected calm. The crust thickened, storms softened, water condensed from steam and rain, gathering into oceans that spread across vast stretches of the young world. Volcanoes still shaped the coastlines, and lightning still danced across the sky, but a sense of stability began to settle over the surface. In this new balance, something remarkable happened. Life appeared with startling speed. From the time the oceans formed to the earliest traces of living activity, only a thin slice of geological time passed. Rocks that had barely cooled from their molten past already held carbon signatures suggesting biological processes. Microfossils emerged not long after, simple in shape but unmistakably the product of living systems. The Earth, still recovering from its violent birth, became home to cells that harvested energy, built membranes, and copied themselves in ways that echoed through billions of years that followed. The rapidity of this emergence raises a quiet, lingering question about the nature of life. Was the rise of biology almost inevitable once the conditions aligned, or was it a rare moment of extraordinary luck, shaped by circumstances so precise they may never repeat elsewhere? Some scientists look to the chemistry of early Earth and see inevitability. Once water pooled across the surface and minerals dissolved into it, the oceans became vast laboratories filled with molecules ready to interact. The planet held energy from sunlight, from vents, and from storms. Simple organic compounds formed through many different pathways, drifting through warm basins and settling on mineral surfaces that shaped them into chains and membranes. In this view, Earth created a setting where chemical evolution did not just happen by chance, but flowed naturally toward complexity. Each reaction opened new possibilities. Each possibility led to others. Given enough time, these steps seemed destined to produce protocells capable of growth and replication. Supporters of this view point to the universality of certain chemical patterns. Amino acids form readily in many conditions, including those simulated in laboratories that mimic early Earth. Components of RNA appear in meteorites and in environments that resemble interstellar clouds. Fatty acids, which create membranes, arise through processes that occur not only on Earth but throughout the cosmos. These patterns suggest that the building blocks of life may be common, and that once they gather in the right environment, chemistry naturally explores pathways that resemble the early steps toward biology. Yet others see rarity instead of inevitability. They note that while many organic molecules form easily, assembling them into a coordinated system is far more challenging. The jump from scattered chemicals to a living cell requires not just the presence of building blocks, but their precise arrangement into a network that can sustain itself. RNA must form strands long enough to store information. Membranes must assemble in ways that protect internal chemistry without blocking essential reactions. Metabolisms must emerge that allow cells to harvest energy reliably. Each of these steps is delicate, and the probability of all of them happening within the same environment at the same time may be far smaller than it first appears. This view also considers the brittleness of early molecules. RNA breaks easily in water. Membranes fall apart under small changes in acidity. Energy sources can destroy the very molecules they help create. The fact that life appeared so quickly on Earth could mean that our planet experienced a rare alignment of conditions, a brief window where everything needed for life existed in the correct balance before being altered by geological shifts. The debate between inevitability and rarity remains open, shaped by the uncertainty of deep time. But the timing of life's emergence offers subtle clues. If life were extraordinarily difficult to produce, requiring countless unlikely steps, one might expect a long delay between the formation of oceans and the appearance of cells. Instead, Earth's earliest life emerged almost as soon as the planet became hospitable. The window between calm seas and biological activity was short, almost as if the planet could not wait to cross the threshold. This does not prove that life arises easily everywhere. It may simply reflect that Earth was uniquely fortunate, but it does suggest that once certain conditions are present, chemistry pushes persistently toward higher complexity. Molecules explore their environments, form bonds, break apart, and form new bonds. Over immense stretches of time, this constant motion may create patterns that resemble purpose, even though the process is guided only by energy and possibility. The rapid appearance of life also reveals something about the nature of the early Earth. The planet was dynamic, rich in energy sources, and filled with wet-dry cycles, mineral surfaces, and gradients that encouraged chemistry to bloom into new forms. It was not a passive world waiting for life, but an active environment shaping the very reactions that would one day take root within cells. In this way, the timing of life's emergence becomes a window into both the generosity and fragility of the early Earth. The planet offered opportunities and challenges, a balance of creation and destruction that guided chemistry toward the first spark of biology. Whether inevitable or rare, the appearance of life happened quickly enough to shape everything that followed, anchoring the future in a moment that arrived long before the world had even finished cooling from its ancient dawn. By the time early life had taken hold and found its quiet rhythm in Earth's young oceans, the planet had already passed through a narrow doorway that few worlds may ever cross. The story so far has moved through stages that felt almost fragile, each depending on conditions that could have shifted with the slightest change in heat, chemistry, or cosmic chance. As we drift forward, it becomes clearer that although life flourished here, the path leading to that moment may not be common across the universe. Stable planets, the kind that can cradle oceans and maintain gentle cycles of warmth and cooling, require a balance that is not easily achieved. A world must orbit its star at a distance where water can stay liquid for long stretches of time, neither locked away as ice nor lost to evaporation. It must form with enough mass to hold an atmosphere, yet not so much that crushing pressure smothers delicate chemistry. It must avoid violent gravitational interactions that tear continents apart faster than life can take root. Even the presence of a large moon, steadying the tilt of our planet and shaping tides, played an unnoticed role in keeping Earth stable enough for fragile molecules to persist. Across the cosmos, many planets orbit their stars too closely or too distantly. Some worlds are bathed in radiation that strips their atmospheres bare. Others lie beneath layers of frozen oceans, too cold for the motions of chemistry to unfold. Stability, the quiet stage on which biology dances, may itself be a rare treasure. Even on Earth, in its earliest chapters, the molecules that formed the foundations of life were astonishingly delicate. RNA strands broke apart under intense sunlight. Primitive membranes lost their structure when exposed to salts or acidity. Amino acids decayed or transformed if the temperature shifted beyond narrow limits. These early ingredients lived on the edge of destruction at every moment. For them to persist long enough to interact, combine, and explore new possibilities required a world capable of offering both protection and freedom. Water played a central part in this balance, yet even water could not be present in excess. It carried molecules, dissolved minerals, and created spaces where reactions could take place. At the same time, it pulled chains apart and prevented long polymers from forming unless the environment dried or concentrated them. Early Earth offered both wet and dry places, shifting in rhythms that allowed molecules to gather, separate, and reform. A world with constant rain or an ocean with no shores might never provide these cycles. Water is necessary, but the way it behaves in partnership with the land may matter just as much as its presence. Energy was another requirement, and it needed to arrive in forms that encouraged complexity rather than chaos. Lightning, sunlight, and the deep heat of hydrothermal vents drove reactions forward, but each of them also had the power to unravel or destroy fragile structures. Too much radiation would break chemical chains before they reached meaningful lengths. Too little would leave them still and unevolved. The early Earth inhabited a rare middle ground, rich in energy yet not overwhelmingly harsh, a place where creation and destruction held each other in a slow, shifting balance. Protective environments, such as the mineral pockets within ancient vents or the clay-lined pools along volcanic shores, offered shelter where molecules could linger and experiment. These microhabitats created pockets of stability within a world that could otherwise be unforgiving. Without them, it is possible that chemistry would never have found enough security to form the long chains that later learned to copy themselves. Yet perhaps the rarest event of all was the emergence of a self-replicator, a molecule capable of creating a version of itself from the resources around it. This step was not simply a chemical reaction, but the beginning of something new. Once copying began, variation followed. Once variation existed, natural selection shaped the future. But the moment that started this cascade may have been the most difficult leap of all. Even with oceans full of building blocks, minerals ready to guide reactions, and stable temperatures across long stretches of time, the formation of a self-replicating system depended on chance arrangements of molecules that may have been extraordinarily unlikely. The right sequence had to appear in the right place, surrounded by the right conditions, stable enough to persist, yet flexible enough to evolve. It required a moment when a fragile chain could recognize itself, hold its shape, and draw the materials needed to continue its pattern. Some researchers believe that such an event could occur many times across the universe, given enough worlds and enough time. Others think the probability might be so low that Earth is one of only a few places where chemistry ever reached that threshold. The truth remains hidden within the silence of distant stars. What the early chapters of our planet reveal is a story shaped not only by possibility, but by constraint. Life needed stability, shelter, energy, and water in just the right forms. It needed molecules that were both cooperative and fragile. It needed a world capable of protecting delicate structures long enough for them to grow into something new. As we move forward, the rarity of these conditions does not diminish the beauty of what came after. Instead, it highlights how many steps were required before Earth could awaken, how many chances aligned so that molecules could learn the arts of memory, growth, and change. By the time the earliest living systems had begun to shape the young Earth, the planet held an immense variety of environments where chemistry moved in countless directions. Warm pools breathed in the sunlight of quiet mornings. Mineral passages deep beneath the seas carried the heat of the planet's interior. Rock surfaces met gentle tides that rose and fell without hurry. Each of these places offered its own version of shelter and energy, its own landscape where simple molecules gathered and rearranged themselves. Within such diversity, it is possible that life did not begin with a single spark, but with many attempts scattered across time and space. Scientists often wonder whether the first successful cells were truly alone or whether other early worlds of chemistry grew alongside them before fading into silence. The idea of multiple origins suggests that Earth may have hosted several beginnings, each rising from different combinations of molecules and energy. Some may have relied on RNA-like strands. Others may have formed from simpler peptides or unstable chains that flickered briefly before dissolving back into the oceans. These early systems might have copied themselves for a short while, leaving no fossil whisper behind. If the planet provided countless small laboratories for chemistry to explore, then it is not difficult to imagine that more than one lineage tried to rise. Yet of all these possibilities, only one survived long enough to shape the future. The lineage that led to the last universal common ancestor carried the traits that endured. It learned to build membranes that protected its inner workings. It developed ways to harvest energy from minerals and gradients. It learned to copy information with enough accuracy to preserve itself, yet enough flexibility to change and evolve. Other early lineages may have lacked such strength. Some may have depended on rare conditions that vanished during storms or shifts in the oceans. Others may have produced molecules too fragile to withstand the heat or radiation of the young planet. A few may have grown in isolated pockets, cut off from nutrient flows, destined to fade when their resources were exhausted. Life requires a delicate balance between shelter and connection, between protection and opportunity, and many early attempts might have fallen on either side of that narrow path. There is a gentle mystery surrounding these vanished possibilities. Because early life left few traces, most evidence lies hidden or erased by the slow churn of Earth's crust. Rocks older than 3.5 billion years are rare, and those that remain have been heated, folded, and transformed so often that their textures no longer carry ancient fossils. If other lineages once lived, their presence would have been washed away long before modern eyes could search for them. Even so, hints of ancient diversity do appear, not in fossils, but in the chemistry of life as it exists today. Enzymes that perform similar tasks sometimes rely on entirely different structures, as if inherited from separate branches of early innovation. Some metabolic pathways look as though they were pieced together from older systems that once functioned independently. These patterns may reflect a world where early cells traded molecules, shared reactions, and competed in quiet currents long before the biological tree took its familiar shape. In this landscape of possibility, the lineage that endured did not necessarily begin as the strongest or the most refined. It may have simply been the one most suited to the long arc of Earth's changing environments. As the planet cooled, as oceans deepened, as minerals shifted through volcanic cycles, only those systems capable of adapting to these changes continued forward. The rest left no descendants, though they may have shaped the world in subtle ways before disappearing. This idea touches on a gentle form of survivorship bias woven through the earliest hours of evolution. When we look backward through time, we tend to imagine that the path leading to modern life was inevitable. Yet we see only the lineage that succeeded, not the many others that may have tried and failed. The chemistry that now feels essential may once have been only one of several routes. The molecules we consider universal may have been chosen by chance, carried forward because they happened to persist in a world that changed around them. If multiple origins did occur, they remind us that Earth's story is not a straight line rising from simplicity to complexity. It is a tapestry woven from experiments, variations, and quiet disappearances. Each lost branch would have contributed to the planet's chemical richness, shaping environments that later supported the lineage that remained. In this way, even the unsuccessful beginnings may have played a part in the arrival of the life we know. As we drift deeper into Earth's ancient past, the idea of many origins becomes not a contradiction, but a reflection of the planet's creativity. The young world offered space for many attempts. Only one endured through the tides of time. As Earth's early environments continued to shift and settle, the boundary between simple chemistry and the earliest traces of life remained thin and delicate, like a veil suspended between possibility and transformation. For countless ages, molecules drifted, collided, and broke apart without intention. They formed patterns guided only by physics and chance. Yet in certain pockets of the planet, these patterns began to behave in new ways, holding themselves together a little longer, shaping responses to the energy around them, and lingering at the edge of something we would one day recognize as living. To understand this transition, it helps to imagine chemistry as a world of restless motion. Molecules float through water or cling to mineral surfaces. They form fleeting structures, then dissolve as soon as conditions shift. Nothing in this realm has a sense of inside or outside. Nothing strives to hold its shape. These reactions simply occur, following the rules of nature without any lasting identity. Life begins when this flow acquires a delicate form of stability. A chemical system crosses a threshold when it begins to maintain itself, to protect its structure against the world beyond it, and to continue its pattern through time. This transformation does not require consciousness or direction. It begins quietly, as certain combinations of molecules show a tendency to preserve their own arrangement even as energy washes through them. There are three traits that mark this threshold, each emerging in its own slow moment. The first is replication. At some point, strands of RNA learn to copy their structure by drawing in nearby building blocks. These early replicators were simple and prone to errors, yet they carried the seed of something extraordinary. They created patterns that did not fade immediately, but returned again and again, anchoring the flow of chemistry in a repeating rhythm. The second trait is metabolism, the gentle choreography of reactions that gather energy and channel it through a system. Long before cells refined these pathways, Earth's early molecules absorbed energy from vents, minerals, or sunlight. Some reactions released small bursts of chemical strength that pushed other reactions forward. In time, these cycles became more coordinated, guiding energy in loops that could sustain a structure rather than scatter it. The third trait is compartmentalization. Membranes of simple fatty acids formed spheres that separated the inside from the outside. These soft boundaries allowed molecules within them to interact more closely and more predictably. A small world appeared inside each droplet, protected from the currents of the ocean or the heat of volcanic shores. Within these tiny shelters, chemistry could linger long enough to build on itself. When replication, metabolism, and compartmentalization came together, a threshold was crossed. A system arose that could grow, maintain its identity, repair damage, and produce new versions of itself. This was no longer merely chemistry, it was the earliest glimmer of biology. Yet perhaps the most profound step in this transition was not replication or energy use, but self-maintenance. A living system is one that tends to preserve the arrangement of its own parts, even as atoms and molecules flow through it. A cell does not simply exist. It continually rebuilds itself, weaving order from the surrounding chaos. This ability to sustain a pattern, moment after moment, is the essence of life. Early protocells likely struggled with this balance. Their membranes sometimes broke apart in salty water, their internal reactions halted when energy flows faltered. Replicating strands could fall victim to heat or radiation, but some combinations were sturdier than others. Some droplets held together long enough to rebuild their membranes. Some strands copied themselves with fewer errors. Some metabolic loops fed back into themselves, creating a gentle stability that endured through changing conditions. As these systems persisted, variation followed. Slight differences in structure led to differences in survival. Some protocells captured resources more readily, others resisted heat more strongly. Over time, these small differences compounded, guiding the earliest forms toward greater resilience. This is where evolution began, not with complex organisms but with subtle shifts in fragile droplets. Each variation created a new possibility. Each possibility met the world's shifting landscapes. Those that faltered vanished quietly. Those that endured shaped the next generation of protocells. Through this slow dance of trial and persistence, the world that had once held only drifting molecules now carried systems capable of learning from their past. In crossing the threshold from chemistry to biology, Earth gained something new, a dynamic layer that responded, adapted, and refined itself. What had once been a scattered collection of reactions became networks that grew more intricate with each passing era. With this transition, the planet changed forever. The oceans no longer held only minerals and molecules. They held the early threads of memory, growth, and change, threads that would one day weave the vast tapestry of life. As we drift deeper into the early history of life, the path that once seemed to unfold with slow clarity begins to soften at the edges. Many steps in this ancient story can be traced through stones, through chemistry, or through patterns held inside modern cells. Yet some pieces remain stubbornly mysterious. They rise like faint shapes beneath deep water, visible only in outlines. Every lineage alive today carries hints of these earliest turning points, but no lineage carries the full memory. What we know is woven from fragments. What we do not know lingers like a quiet echo beneath the tale. One of the most striking puzzles rests within the structure of RNA itself. Among its components is a sugar called ribose, a delicate and unstable molecule that rarely forms on its own. In modern laboratories, ribose appears only under narrow conditions, often with the help of minerals or specific cycles of drying and warming. On the early Earth, where heat, water, and ultraviolet light constantly shifted, ribose would have been even more fragile. It breaks apart easily, and without protection, it cannot survive long enough to build complex strands. Yet RNA, with ribose at its core, played an essential role in the earliest forms of life. This contradiction rests at the heart of the mystery. If ribose forms so rarely and decays so quickly, how did enough of it accumulate to create RNA in the first place? Some researchers suggest that mineral surfaces may have sheltered ribose from destruction. Others look toward environments with repeated wet and dry cycles that could have encouraged ribose to form in short bursts. But no single explanation fits comfortably. The origin of ribose remains one of the quiet gaps in our understanding, a fragile piece of the puzzle that still waits for clarity. Connected to this is the origin of the first nucleotides, the building blocks of RNA. Nucleotides are not simple molecules. Each one carries a sugar, a phosphate, and a nitrogen-rich base arranged in a way that allows strands to copy information. The formation of nucleotides requires several steps, each dependent on conditions that must align with remarkable precision. Today, cells craft nucleotides with the help of enzymes, intricate tools that did not exist in the earliest chemical world. Where, then, did the first nucleotides come from? Some experiments show that parts of nucleotides can form naturally in environments rich in ultraviolet light. Others reveal that certain minerals can bring components together. There is even evidence that meteorites carried some of these pieces to Earth. Yet none of these explanations fully closes the gap. How these components combined in the right place, at the right time, remains an open question. It is as though early Earth gathered ingredients from many scattered sources, but the recipe it followed has been lost to time. Another mystery lingers in the rise of enzymes. Today, enzymes are the engines of life. They shape the speed and flow of reactions inside every living cell. Without them, biological chemistry would be slow and uncoordinated, yet enzymes are usually proteins, long chains of amino acids folded into precise shapes. Their complexity is astonishing. The first living systems could not have relied on proteins as advanced as the ones we see today. Something simpler must have come first. Some scientists believe that ribozymes, RNA molecules with catalytic abilities, filled this early role. They could speed up reactions and encourage new bonds to form. However, ribozymes themselves are limited. They can perform only a small range of tasks compared to modern enzymes. At some point, life moved from these modest tools to the intricate proteins we now observe. How this transition occurred, how the earliest proteins emerged, and how their folds learned to shape chemistry with such precision is still unknown. The pathway from simple catalysts to full enzymatic machinery likely took place in countless small steps, each one favored by survival. But the details remain hidden. There are no fossils of molecules. There is no record of the first protein fold. What we know must be rebuilt by inference, through the shadows cast by the enzymes all organisms use today. Beyond these puzzles lie many others. How did the first protocells keep their fragile structures intact when conditions shifted? How did early metabolisms link together into networks stable enough to support growth? Why did certain chemical pathways endure while others disappeared without leaving a trace? And at the broadest scale, why did Earth succeed where so many worlds may not? Current models offer glimpses rather than complete stories. They show what is possible, not what certainly happened. They reveal routes that chemistry can explore, but they cannot trace the exact path life took in its earliest moments. Some questions may remain unanswered simply because time has erased the evidence. Others may be waiting for experiments that have not yet been imagined. In these uncertainties lies a quiet wonder. The gaps in our knowledge do not weaken the story. They give it depth, reminding us that life's beginning was not a single moment, but a vast landscape of possibilities. Some realized, many lost. Even now, as we uncover new clues from ancient rocks and explore the boundaries of chemistry, the earliest steps of life remain partly veiled, inviting us to listen closely to the echoes of a world still learning how to live. As we step gently from the ancient world into the present day, the story of life's beginning does not end. Instead, it continues in quiet laboratories where glass vials shimmer beneath soft lights, and where researchers try to recreate moments that unfolded billions of years before any eye could witness them. In these still rooms, Earth's earliest chapters are explored not with memory, but with imagination guided by chemistry. Each experiment is a small window into the world as it once was, a way to touch the processes that shaped everything alive today. One of the most evocative efforts lies in the creation of protocells, simple droplets that mimic the earliest cell-like structures. Scientists mix fatty acids and water in controlled conditions, and before long, tiny spheres begin to form on their own. These droplets curve inward, creating a small interior space that separates its contents from the outside world. In the soft glow of a microscope, they pulse gently as molecules drift in and out, imitating the earliest whispers of a living boundary. When researchers add strands of RNA or basic metabolic components to these droplets, something remarkable happens. The molecules inside behave differently from those left free in solution. They cluster together. They react more efficiently. They linger long enough to spark new chemical steps. Though these protocells lack the complexity of even the simplest modern cell, they recreate the quiet shelter that early life might have known, a world where fragile chemistry could persist long enough to grow. In another corner of Origins research, artificial ribozymes bring the past even closer. Ribozymes, those rare RNA molecules that act like enzymes, remind us that before proteins shaped the rhythms of life, RNA may have taken the lead. Modern scientists design ribozymes with specific tasks, such as cutting or copying short strands of RNA. In small reaction chambers, these artificial molecules perform their duties with surprising finesse, stitching together fragments or guiding chemical flows with a precision that echoes ancient biological rhythms. Some ribozymes even show glimpses of self-improvement. Through careful selection, researchers nudge them toward greater efficiency, watching as each new generation folds a little differently, reacts a little faster, or holds its shape more firmly. These experiments offer hints of how natural selection might have acted at the molecular level long before living cells existed, shaping early chemistry into something more persistent and capable. Deep beneath many laboratories, in chambers designed to mimic hydrothermal vents, another line of exploration unfolds. These simulators recreate conditions near underwater vents where heated fluids rise from the crust, rich with minerals and steep chemical gradients. In metal cylinders lined with porous material, scientists circulate water infused with iron, sulfur, and carbon sources. Temperatures rise and fall along the chamber walls, recreating the gradient of a real vent. Within these artificial vents, something quietly stirring emerges. Simple organic molecules begin to form. Carbon dioxide transforms into small chains. Minerals catalyze reactions that resemble primitive metabolic pathways. Some experiments even produce tiny compartments within the mineral surfaces, spaces that look remarkably similar to the pores that might have sheltered early chemical networks. These simulators provide a glimpse of how Earth's interior could have cradled the first reactions that later blossomed into life. Each of these experiments offers a fragment of understanding. Protocells reveal how boundaries might have formed. Ribozymes show how information and catalysis might have intertwined. Hydrothermal simulators reflect how energy and minerals could have fueled early cycles. Together, they create a mosaic of possibilities, a collection of scenes that bring the ancient world a little closer. Yet these attempts also reveal the limits of our knowledge. Even with modern tools, it remains difficult to coax chemistry toward the full complexity of life. Protocells do not yet replicate in ways that persist through many generations. Artificial ribozymes accomplish only a narrow range of tasks, far less than what early life would have needed. Hydrothermal simulators produce building blocks, but they do not create systems that maintain themselves or evolve in open-ended ways. In every experiment, there is a boundary we cannot yet cross. We can form pieces of the puzzle, but assembling them into a unified, living whole remains beyond reach. Some of the steps that occurred on the early Earth may have relied on conditions far more varied and dynamic than any laboratory can replicate. Others may have taken place over stretches of time longer than any experiment can run. Still others may have required a kind of chemical serendipity that is difficult to reproduce in a controlled environment. Even so, each attempt deepens our understanding. Every protocell that forms, every ribozyme that folds, every mineral surface that guides a reaction offers a clue to the immense creativity of early Earth. These experiments do not seek to create life as it is now. Instead, they allow us to glimpse life as it might once have been, fragile and uncertain, shaped by energy and chance, yet inching slowly toward the patterns that would define the future. In this gentle interplay between past and present, the laboratories of today become a quiet continuation of Earth's ancient story, reflecting not only what life became, but how it might have first begun to stir. As the story of Earth's beginnings stretches forward, it naturally reaches a place where our gaze turns outward. The same curiosity that once followed drifting molecules across volcanic shores now travels beyond our planet, carried by telescopes, probes, and quiet anticipation. After tracing the delicate steps that allowed life to take shape here, we begin to wonder whether those steps might have unfolded elsewhere, in hidden oceans or beneath distant skies. The search does not come from doubt, but from the gentle realization that Earth may not be the only world where chemistry found its way towards something more. Among all the places in the solar system, few stir the imagination as deeply as Europa, one of Jupiter's large moons. On its surface, Europa appears silent and pale, wrapped in a crust of ice etched with dark lines that stretch for hundreds of kilometers. But beneath this frozen shell lies a global ocean, kept warm by the tug of Jupiter's gravity. Scientists believe this ocean may hold more water than all of Earth's seas combined, a vast and shadowed realm that has remained hidden for billions of years. In this darkness, warmth rises from the moon's rocky floor, much like the hydrothermal vents that once shaped Earth's early chemistry. Minerals dissolve into the water, energy flows through cracks and fissures. If life needs shelter, water, and energy, Europa offers all three in abundance. No sunlight reaches these depths, but just as early microbes on Earth once thrived without light, Europa's ocean may contain places where chemistry leans toward complexity. We do not yet know what moves through those waters, if anything at all. But the possibilities ripple gently beneath its ice, waiting for the moment when a spacecraft can touch down, drill through, or listen for signs hidden in the tides below. Farther away circles Enceladus, a small moon of Saturn that glows softly against the darkness. Its icy surface is marked by long blue fissures near the South Pole, places where the crust stretches and opens. From these fractures, plumes of water erupt into space in graceful arcs, carrying ice crystals, salts, and organic molecules. When spacecraft flew through these plumes, they detected signs of hydrothermal activity deep underground, suggesting that Enceladus too holds a hidden ocean with warmth rising from its rocky interior. These rising waters resemble, in spirit, the environments that once sheltered early Earth. They contain the minerals needed for organic chemistry. They cycle through pressure and heat. They carry hints of simple carbon-based compounds, tiny messengers from a world we cannot yet see directly. To imagine hydrothermal-like vents beneath Enceladus is to imagine a place where chemistry may gather in sheltered pockets, perhaps forming patterns that persist for moments or for ages. Even if life has not yet emerged there, the ingredients and energy create a stage where such a story could begin. Then there is Titan, Saturn's largest moon, wrapped in a thick golden haze. Titan is colder than any place where Earth-based life could survive, yet it holds rivers, lakes, and seas made of liquid methane and ethane. These strange waters ripple beneath a sky filled with complex organic molecules. On Titan's surface, grains of solid hydrocarbons drift like dark sand. In its atmosphere, sunlight and methane interact to create a rich tapestry of chemistry unseen anywhere else in the solar system. Titan is unlike Europa or Enceladus. It may not hold liquid water on its surface. Instead, it offers a world where chemistry explores entirely different paths, guided by cold rather than warmth, by methane instead of water. Some researchers imagine that Titan could host forms of life built on unfamiliar molecules, perhaps slower and more fragile, shaped by temperatures near absolute stillness. Others focus on its deep subsurface ocean, where liquid water might mix with ammonia, to create a warm refuge beneath the frozen crust. Titan reminds us that life, if it exists elsewhere, might not resemble the forms we know at all. Its landscapes hint at possibilities not bound to Earth's patterns. Across these moons and beyond, the search for another origin of life carries profound meaning. Finding even the faintest sign of biology elsewhere, whether in a drop of European water, a grain of Enceladine ice, or a chemical fingerprint drifting through Titan's air, would reshape our understanding of existence. It would show that life is not a solitary event confined to one blue world, but a natural outcome of chemistry wherever the right conditions gather. It would expand the story we have followed, revealing that Earth's fragile beginnings were not unique, but part of a broader chorus echoing across the cosmos. And even if we find no living systems, the search itself deepens our connection to the universe. Each ocean, plume, and cloud of organic haze invites us to imagine different worlds moving through their own silent ages. These distant places hold their secrets patiently, much as Earth once did, waiting for the moment when light, curiosity, and gentle wonder finally reach them. As we look back across the long curve of Earth's early history, a quiet realization begins to form. Life did not emerge in a world prepared for it. It arose in a landscape filled with shifting seas, unstable climates, and delicate chemistry that could have failed at any moment. The steps that carried simple molecules toward living systems were narrow, uncertain, and easily broken. Yet somehow, through all this fragility, life persisted long enough to take root, to endure, and eventually to flourish. The earliest cells lived in a world balanced on the thinnest of edges. For them to survive, only a few conditions needed to be just right. The oceans had to hold the proper mixture of minerals and temperature. The atmosphere had to shield harmful radiation without blocking the energy needed for chemistry. The planet's crust had to remain stable enough to support shallow environments where reactions could gather and grow. Even the cycles of day and night, of wet and dry, played roles that shaped the possibilities available to early life. Had any of these conditions drifted too far in either direction, the story could have ended almost before it began. A slightly hotter climate could have broken apart fragile membranes. A slightly colder surface could have locked essential molecules beneath layers of ice. A thinner atmosphere could have allowed ultraviolet light to tear apart the building blocks of RNA. A thicker one could have smothered delicate reactions. The space for life was neither wide nor forgiving. It was a gentle window, open for only certain temperatures, certain pressures, certain chemical balances. Within this narrow window, countless steps had to unfold in just the right order. Molecules needed to gather, then link, then fold. Membranes needed to form at the right moments, enclosing fragile reactions before they dissolved. Replicating systems had to appear before the environments that sustained them shifted. Metabolisms had to learn to harvest energy without destroying themselves. At every stage, there were many more ways for the process to fail than to succeed. If the first replicating strands had broken too quickly, evolution could never begin. If early protocells had drifted into conditions they could not endure, there would be no descendants to carry their story forward. Even after life stabilized, it faced challenges that threatened to erase all progress. Asteroid impacts, shifting climates, and changes in ocean chemistry all rose like waves that could have swept the earliest lineage away. Yet each time, life found a small place to hide, to recover, and to continue. Deep below the surface, microbes sheltered in warm rock as the world above them changed. In the oceans, communities held together even when temperatures shifted or minerals ran low. These early survivors explored every corner of possibility, adapting slowly to the rhythm of a planet still shaping itself. Their persistence was not guaranteed. It was the outcome of billions of small interactions, each one holding the potential to continue a pattern that stretched into the future. When we look at the steps that shaped life, it becomes clear how easily things might have turned out differently. If ribose had been slightly harder to form, RNA might never have taken shape. If membranes had been more fragile, protocells might have torn apart before they could learn to replicate. If early enzymes had not stumbled toward efficiency, chemistry might have remained still and scattered. Even the first division of labor between DNA, RNA, and proteins relied on transitions so delicate that they could have failed at many points. Yet, through all these fragile stages, life did not vanish. Instead, it strengthened itself, gradually widening its path through time. What began as uncertain chemistry grew into stable lineages. What began as fleeting reactions became cycles that endured for generations. Little by little, life stepped away from the edge and began to build the world we now know. Every organism alive today carries the echoes of this unlikeliness. Each cell and every creature belongs to a chain that reaches back to the first spark, untouched and uninterrupted across billions of years. No lineage broke that chain. No generation failed to pass its memory forward. Through tidal shifts, volcanic winters, and global transformations, life continued without missing a single step. This continuity is among the most astonishing truths of our planet's history. From the earliest protocells drifting in ancient seas to the forests, oceans, and mines that exist now, everything is connected by a line that has never been severed. Every living thing belongs to the same story, beginning with fragile molecules that learned to endure in a world that offered them little certainty. As the narrative flows forward, this unbroken chain becomes more than a scientific detail. It becomes a reminder of how much had to hold together for life to remain, how narrow the path truly was, and how extraordinary it is that the story continued long enough for us to tell it. As our long journey through Earth's earliest chapters draws to a close, we find ourselves standing at the edge of a mystery that has accompanied us from the beginning. We have moved through molten landscapes and quiet oceans. We have drifted beside fragile molecules as they learned to hold their shapes, and followed the first replicators as they explored the narrow space between survival and disappearance. We have watched protocells gather courage in warm pools and traced the threads that connect every organism alive today back to a single unfolding moment. Yet, even with all we have uncovered, the origin of life remains partly hidden, resting in a place beyond the reach of any fossil or experiment. The deeper we travel into this story, the more we see how much remains unsolved. And strangely, this uncertainty does not diminish its beauty. It adds to it, weaving wonder into each unanswered question. The mystery survives because life itself is a pattern shaped by countless chances, each one delicate, each one improbable, each one necessary. What we do know is that on a quiet night billions of years ago, Earth crossed an invisible threshold. Simple chemistry, stirred by heat and minerals and shifting seas, arranged itself into something capable of memory and change. A spark that was not fire but pattern, not light but persistence, began rewriting the destiny of the planet. That moment, buried in time, still echoes through every living thing. It exists in the way cells divide, in the way ecosystems breathe, in the way DNA carries whispers from the distant past. Every heartbeat, every leaf unfolding, every microbe drifting through the ocean carries a faint trace of that ancient dawn. We now understand that the story of life is not only about success, it is also about delicate escape. Life survived meteor strikes, volcanic winters, shifting atmospheres, and long stretches of uncertainty. It emerged not because the world was ready for it, but because the world offered just enough room for something fragile to endure. Through that endurance, everything we know took shape. Standing at the end of this journey, it is natural to wonder what pieces still lie hidden. How did ribose form under early skies? What guided the first nucleotides into place? Where did the earliest metabolisms find their rhythm? These questions linger softly, waiting for new insights, new experiments, and new imaginations to approach them. The beauty of science is that it does not close its doors when answers remain incomplete. Instead, it invites curiosity to step forward. It welcomes each new perspective, each gentle hypothesis, each thoughtful question. The story becomes richer each time someone pauses to consider how life might have begun, or what paths it might have taken before settling into the lineage that ultimately shaped us. So, as we bring this calm journey to a close, I would love to hear your thoughts. What parts of Earth's earliest history resonate with you? Which possibilities feel most vivid when you imagine the world before life? Do you see the beginnings unfolding in warm pools, in the depths of ancient oceans, or across mineral landscapes touched by sunlight? Your reflections add depth to this shared exploration, and I read them with gratitude. If you have enjoyed drifting through these ancient mysteries, gently exploring the edges of knowledge and imagination, I invite you to stay with us for future journeys. There are countless stories still waiting in the quiet corners of science, each one filled with wonder, each one unfolding at a pace meant to soothe the mind. A gentle like or a soft tap on the subscribe button helps more curious wanderers find their way here, to this calm space where we explore the universe one peaceful thought at a time. As we end this chapter, take a slow breath. Notice how the story you have followed stretches across billions of years, yet settles lightly in the present moment. The origin of life may remain mysterious, but it is a living mystery, one that surrounds us in every tree, every bird, every strand of DNA. And tomorrow, new ideas and discoveries will continue the tale. For now, let us rest in the knowledge that the night Earth learned to make life still moves through everything. And as long as curiosity survives, the story will keep unfolding quietly and beautifully just beyond the edge of what we know.